waists, but, for various reasons, a longitudinal extension is less damaging to the propellant. As I seem to remember, this idea about rockets stemmed from the bias-cut 90s which were around at the time. The strain requirements for rockets are generally just the opposite of what is needed in blood vessels. As we saw in Chapter 8, one wants an artery to maintain a constant length while exposed to fluctuations in blood pressure, but changes in artery diameter are not important. Either condition can be met by making suitably designed tubes from helically disposed fibers. Problems of this kind keep cropping up in biology, and it was most interesting to find that Professor Steve Wainwright of Duke University, who is concerned with worms, has derived, quite independently, just the same mathematics as we had worked out 20 years or so before for use in rocketry. On inquiry, I find that in this case too the inspiration arose, via Professor Biggs, from the bias cut. The invention of the bias cut brought fame to Mile Vianet in the world of haute couture. She lived to a great age and died, not long ago, at 98, quite unaware of her very significant contributions to space travel, to military technology and to the biomechanics of worms. Shear stress is only tension and compression acting at plus or minus 45 degrees, and vice versa. A very little further thought about plate webs in beams and lattice webs in trusses and about bias-cut 90s makes it obvious that a shear stress is merely tension or compression, or both, acting at 45 degrees, and that, furthermore, there is a shear stress acting at 45 degrees to every tension and compression stress. In fact, solids, especially metals, very frequently break in tension by reason of the shear stress at 45 degrees. It is this which leads to the necking of metal rods and plates in tension and to the mechanics of ductility in metals, Figure 9 and Chapter 5. As we shall see in the next chapter, very much the same thing can also occur in compression. That is to say, many solids break in compression by sliding away from the load in shear. Creasing or the Wagner tension field. A thick plate or a solid piece of metal is able to resist compression, and so, when such things are subjected to shearing loads, there will exist, at plus or minus 45 degrees, both tension and compressive stresses. Thin panels and membranes and films and fabrics are scarcely able to resist compression forces in their own plane, and so, when they are sheared, they are apt to crease. This creasing in shear is quite common in thin metal panels, such as occur in aircraft, and it is quite usual to see a creased or quilted effect on the surfaces of wings and fuselages due to this cause, Plate 19. This is called by engineers a Wagner tension field. Figure 9. In ductile materials both tension and compression failure tend to occur by shear. The same effect is even more common in clothes and loose covers and tablecloths and badly cut sails. I suppose dressmakers do not very often talk about Wagner tension fields, but they do. Sometimes refer to that slightly mysterious quality which is known in the textile trade as drape. The drape of a fabric depends mainly upon its shear modulus, and although, very probably, few couturiers could quote any figures, in SI or any other units, for the shear modulus, G, of their silks and cottons, on the whole, the lower the shear modulus of a material, the less its tendency to unwanted creasing. The reason why we cannot dress ourselves in paper or cellophane without appearing ridiculous is mainly that these substances have too high a shear stiffness, so that they will not drape properly. Contrariwise, knitted and crepe fabrics have both a low Young's modulus and a low shear modulus, so that it is easy to get a close and flexible fit, as girls have discovered with knitted sweaters. In the same way the skin of young people has a low initial Young's modulus and a low shear modulus and therefore conforms easily to the shape of the body. In later life the skin becomes stiffer in shear, with obvious results. Recently Professor R.M. Kennedy of the University of Strathclyde has made an extensive study of elastic conformity in human skin. So, for the first time, the wrinkles of age are likely to be put onto a numerical or quantitative basis. Torsion or twisting. The aeroplane was developed from an impossible object into a serious military weapon in something like 10 years. This was achieved almost without benefit of science. The aircraft pioneers were often gifted amateurs and great sportsmen, but very few of them had much theoretical knowledge. Like modern car enthusiasts, they were generally more interested in their noisy and unreliable engines than they were in the supporting structure, about which they knew little and often cared less. Naturally, if you hot up the engine sufficiently, you can get almost any aeroplane into the air. Whether it stays there depends upon problems of control and stability and structural strength which are conceptually difficult. In the early days too many brave men, like C.S. Rolls and S.F. Cody, paid with their lives for this attitude of mind. The theoretical basis of aerodynamics had been worked out by F.W. Lanchester in the 1890s, but not many practical men had the least idea what he was talking about. A good many of the accidents to the pioneers were caused by stalls and spins, but structural failures were nearly as common. Since the early pilots seldom used parachutes, these accidents were generally fatal. The requirement for a really reliable lightweight engineering structure was, of course, more or less a new one. In the first place, the wings of an aircraft are subject to bending forces, very much like a bridge. Since this is obvious, and since there was a good deal of precedent to go on in the matter of bridge construction, bending loads could generally be dealt with more or less safely. What was not so often realized was that the wings of an aeroplane are, in addition, subject to large torsional or twisting forces. If no proper provision is made to resist these torsions, the wings will be twisted off. With the expansion of military flying after war broke out in 1914, the accident rate became a serious matter. In this country, luckily, such questions were dealt with by that small group of brilliant young men at Farnborough who afterwards became famous as Lord Cherwell, Sir Geoffrey Taylor, Sir Henry Tizard and Jehovah Green. Thanks to their efforts, the traditional biplane became, by 1918, one of the safest of all structures and came to be regarded as almost unbreakable. The Germans were less fortunate. Their aircraft technical authorities at that period had the reputation of being rather hidebound. At any rate, they had a long run of structural accidents, many of them due to a failure to understand the problem of torsion in aircraft wings. By the early part of 1917, the Allies had achieved a degree of air superiority on the Western Front, partly as a result of the technical quality of their fighters. However, in the meantime, the very able designer Anthony Fokker was developing an advanced monoplane fighter, the Focker D8, with a performance better than anything available or in immediate prospect on the Allied side. Because of the critical tactical situation, production of the D8 was accelerated and it was issued to several of the crack German fighter squadrons without undergoing any adequate program of test flying. As soon as the D8 was flown under combat conditions, it was found that, when the aircraft was pulled out of a dive in a dogfight, the wings came off. Since many lives were lost, including those of some of the best and most experienced German fighter pilots, this was a matter of very grave concern to the Germans at the time, and it is still instructive to study the cause of the trouble. In those days most aircraft were biplanes, because this form of construction was lighter and also more reliable. However, for a given engine power, a monoplane will generally be faster than a biplane, because it does not have to experience the extra air resistance resulting from the aerodynamic interference which occurs between two adjacent sets of wings. There was thus a strong inducement to build monoplane fighters. However, although the reasons for the many failures were not understood, monoplanes had been known to be structurally unreliable ever since the wings of Samuel Langley's historic aeroplane had collapsed over the Potomac River in America in 1903. The wings of the Focker D8, like those of most monoplanes at the time, were fabric covered. The fabric was there solely to provide the desired aerodynamic shape. It was merely stretched over an internal structural framework and itself carried none of the main loads. The main bending loads were taken by two parallel wooden spars or cantilever beams which projected sideways from the fuselage. The two spars were connected every few inches by a series of light-shaped wooden ribs, to which the doped fabric was attached, Figure 10. As soon as the accidents to the D8 became known, the German Air Force authorities very naturally ordered structural tests to be made. After the custom of the time, a complete aircraft was mounted upside down in a test frame, and the wings were loaded with piles of shot bags, disposed so as to simulate the aerodynamic loads which occur in flight. When tested in this way, the wings showed no sign of weakness, and they were broken only by a load which was equivalent to 6 times the total loaded weight of the aircraft. Although nowadays fighter aircraft are required to withstand a load equivalent to 12 times their own weight, in 1917 a factor of 6 was considered entirely adequate and almost certainly represented a bigger load than would have occurred under the worst combat conditions at the time. In other words, the aircraft should have been perfectly safe. Figure 10. Fabric-covered monoplane wing. However, in the D8, when structural collapse did eventually happen on the test rig, the failure could be seen to begin in the after of the two spars. To make quite certain, therefore, the authorities ordered the rear spars of all Focker D8s to be replaced by thicker and stronger ones. Unfortunately, after this had been done, the accidents became more, not less, frequent, and so the German Air Ministry had to face the fact that by strengthening the wing by adding more structural material they had actually made it weaker. By this time it was becoming clear to Anthony Fokker that he was not going to get much effective help from the official mind. He therefore loaded up another D8 under his own supervision in his own factory. This time he took care to measure the deflections which occurred in the wing when it was loaded. What he found was not only that when the wing was loaded it deflected in bending, that is to say, the wingtips would rise with respect to the fuselage when the plane was pulled out of a dive, but also that the wings twisted although no obvious twisting loads had been applied to them. What was particularly important was that the direction of this twisting was such that the aerodynamic incidence, or angle of attack of the wing, was significantly increased. Pondering over these results that night, it suddenly occurred to Fokker that here lay the solution to the D8 accidents and to a great many other monoplane troubles as well. When the pilot pulled the control stick back, the nose of the plane rose and so did the load on the wings. But at the same time the wings twisted, so that air loads on the wings rose disproportionately, so the wings twisted more, so the loads rose still more, and so on, until the pilot no longer had any control over the situation and the wings were twisted off. Fokker had discovered something which is called a divergent condition, which can also be a very lethal one. What was actually happening in terms of elasticity? Centers of flexure and centers of pressure. Consider a pair of similar, parallel, cantilever beams or wing spars, joined together at intervals by horizontal fore and aft ribs bridging the gap between them, Figure 10. Suppose now a single upward force to be applied at some point on one of the outer ribs. Unless this force is applied at a point which is just halfway between the two cantilever spars, Figure 11, the load will not be equally shared between the spars and the upward force will be greater on one spar than on the other. If this happens, then the more heavily loaded spar must deflect upwards further than its partner, Figure 12. In such a case the ribs joining the spars will cease to be horizontal and the wing as a whole must twist. The point at which a load must be applied so as to cause no twisting in a beam-like structure is called the center of flexure or the flexural center. Figure 11. Coupled bending and torsion. Only if the vertical lift forces act effectively at a point called the flexural center, in this case halfway between the two spars, will the wings bend upwards without twisting. Naturally, if there are more than two spars, or if the spars are of differing stiffness, then the flexural center will not be at the midpoint but at some other position along the fore and aft or chord line. However, there is always a center of flexure associated with every sort of beam or beam-like structure. A vertical load applied at this point will not cause the beam or wing to twist. A load applied at any other fore and aft position will cause a greater or less amount of twisting or torsional deflection as well as the usual bending deflection. So far we have argued the case in terms of a single point load applied to a beam or a wing. Naturally, the aerodynamic lifting forces which, when an aircraft is in flight, press upwards on a wing and so keep the machine in the air are diffused over the whole of the wing surface. However, for the purposes of discussion and calculation all these forces can be considered as acting together at a single point on the wing surface which is known as the center of pressure CP. Figure 12. If the lift forces act at a point away from the flexural center, e.g. near the leading edge of a wing, then the wing, or any other beam, will twist as it bends. If this causes an increase of aerodynamic incidence the result may be fatal, as it was in the Focker D8. It might perhaps be supposed by the uninitiated that the CP of the lift forces acting on a wing in flight lay at the middle of the wing, halfway between the leading and trailing edges, that is to say, at mid-chord. Actually it is a well-known fact of aerodynamic life that this is just what does not happen. The center of pressure of the lift forces on a wing is really not far behind the leading edge, usually near to what is called the quarter-chord position, that is to say, 25% of the chord behind the leading edge. It follows that, unless the structure of the wing is designed so that the flexural center is close to the quarter-chord position, the wing must twist. The angle through which the wing will twist will naturally depend upon how stiff the wing is in torsion, but, on the whole, all wing twisting is a bad and dangerous thing in an aeroplane and it is the designer's aim to reduce it as much as possible. This is why the quill of a bird's wing feather is usually located around the quarter-chord position. Figure 13. Figure 13. Lift distribution across an aerofoil. In a simple fabric-covered monoplane wing both the position of the center of flexure and also the torsional stiffness depend almost entirely upon the relative bending stiffnesses of the main spars. In the Focker D8 the center of flexure was a long way behind the center of pressure and much too near mid-chord. The wing had not enough stiffness to resist the resulting torsional forces and so it was twisted off. Modifications which strengthened and stiffened the rear spar had the effect of moving the flexural center still further backwards and so made the situation even worse. When these facts dawned on Anthony Focker he took the by now obvious step of reducing the thickness and stiffness of the rear spar, thus moving the center of flexure further forward and closer to the CP. When this was done the D8 became, comparatively speaking, a safe machine and a menace to the Royal Flying Corps and the French Air Force. Because of the laws of aerodynamics the CP of the lift forces acting on an aeroplane wing must always be near to the quarter-chord position. To reduce the torsional or twisting stresses in the wing it is therefore necessary to design the structure in such a way that the center of flexure is well forward in the wing and lies close to the CP. However, the ailerons, which control the aircraft in roll, that is to say, when banking, apply large up or down forces to the wingtips, and these forces act at points not far from the trailing edge and thus a long way to the rear of the center of flexure. Thus the ailerons inevitably exert large twisting loads on the wings every time the pilot banks the aircraft. It will be seen from figure 14 that the direction of this twist is such as to change the aerodynamic lift on the wing, as a whole, in the opposite sense to the action of the aileron and thus to reduce its effect. If the wing is not sufficiently stiff in torsion the effect of the aileron may actually be reversed, so that the pilot, wanting to roil or bank the aircraft to the right, and applying his controls in that sense, may find that the aircraft actually rolls to the left. This effect, which is not only disconcerting but also very dangerous, is called aileron reversal and is not unknown. It is a serious problem in the design of modern fast aircraft. The cure or preventive is to ensure ample torsional stiffness in the wing structure. Figure 14. An aileron applies large vertical loads near the trailing edge of a wing and well aft of the wing's flexural center. It therefore tends to twist the wing in such a way as to provide aerodynamic forces which are the opposite of those desired by the pilot. In the early fabric-covered monoplanes, such as the D8, the torsional stiffness of the wings was almost entirely due to what is called the differential bending of the two main spars. Not very much can be done about this, and the amount of torsional stiffness which can be obtained from such a system, even with the help of a certain amount of wire rigging, is quite limited. For this reason such aircraft were always more or less dangerous, so much so that the authorities in nearly every country frowned on monoplane construction, and in some cases it was actually forbidden. The preference for biplanes was, therefore, not due to some kind of reactionary stupidity on the part of air ministries, but rather to the fact that the biplane provides what is inherently a stiffer and stronger form of construction, especially in torsion. In practice, biplanes were both lighter and safer than monoplanes for many years, and in the early days the difference in speed was not very great. What the strutted and braced biplane construction does is to provide, in effect, a sort of cage or torsion box which is very strong and stiff, not only in bending but also in torsion. From figure 15 it will be seen that the four main spars, two in each wing, run along the corners of the box, while the spaces between them form a braced truss or lattice girder. One does not, of course, see the diagonal bracing on the top and bottom surfaces, because it is hidden by the fabric of the wings. However, this horizontal bracing is there all right, and its function is to take the shears which arise from the torsions in the wing structure. The manner in which such a box can resist torsion is shown diagrammatically in the figure. It will be seen that each side of the box is being sheared individually, very much like the lattice web of a trussed beam which is in bending. Notice that all four sides of the box are being sheared together and that they are mutually dependent. If one of the four sides were cut or removed there would be no resistance at all to torsion. Figure 15. Diagram of the main structure of a pair of wire-braced biplane wings subject to torsional forces, e.g. from the ailerons. The whole affair forms what is called a torsion box. In a biplane these shear panels are necessarily made from struts and wires. However, if the structure did not have to fly but merely had to resist torsional forces on the ground, then the lattice of wires and struts could be replaced by continuous panels of metal or sheets of plywood. From a purely structural point of view the effect would be the same, just as it would be in the web of a beam truss. Torsion can therefore be resisted by any kind of box or tube whose sides may be continuous or alternatively of openwork lattice construction. In either case the walls or sides of the tube are subject to shearing stresses. In terms of weight and strength and stiffness this is a very much more effective way of resisting torsion than depending on the differential bending of two beams. Formulae for the strength and stiffness in torsion of various kinds of rods and tubes are given in Appendix 3. Among other things it will be noticed that the strength and stiffness in twisting of a tube or torsion box depends upon the square of the area of its cross-section. Thus a torsion box of large cross-section, such as an old-fashioned biplane, will require little material and will be light in weight. When we build a modern monoplane, what we do is to turn the wing itself into a torsion tube with a continuous covering of metal sheet or plywood. However, even though we, perforce, use a much thicker wing than was the practice with biplanes, yet the cross-sectional area of the torsion tube, as a whole, is still much less than that of the biplane. So to get adequate torsional strength and stiffness we are forced to use comparatively thick and heavy skin. Thus a comparatively high proportion of the weight of the structure of modern aircraft has to be devoted to resisting torsion. Although a lack of torsional stiffness is not quite as dangerous in cars as in aircraft, the character of a car's suspension and road holding does largely depend upon it. The pre-war vintage cars were sometimes magnificent objects, but, like vintage aircraft, they suffered from having had more attention paid to the engine and the transmission than to the structure of the frame or chassis. These chassis, in fact, usually relied for any torsional stiffness which they might have had upon the differential bending of rather flexible beams, much like the old Focker D8. It was the lack of stiffness in the chassis which gave these cars their highly uncertain road-holding characteristics and which made them so tiring to drive. In an attempt to keep the wheels more or less in contact with the ground, the springs and shock absorbers of the vintage sports cars were stiffened up until they were virtually solid. As a result, of course, the ride became almost unbearably rough and jerky. Like the noisy exhaust, this kind of thing was no doubt impressive to the girl passenger, but it did not really do very much to keep the car on the road. The solution adopted by most modern car designers is to scrap the rather flimsy chassis and to take the torsion and bending loads through the pressed steel saloon body shell. This forms, with its roof, a big torsion box not wholly unlike the old biplanes. With so much stiffness at his disposal, the designer can concentrate on providing a scientifically designed suspension which is both safe and comfortable. As we have said, the strength and stiffness of a structure in torsion vary as the square of the area of its cross-section. This is more or less alright with bulky things like aircraft wings and ships' hulls and saloon cars. But when we come to shafts in engines and machinery, the diameter, and therefore the area of the cross-section, is usually very limited, and so, as a rule, such members need to be made from solid steel. Even then, although they are often very massive, they are not always sufficiently strong. This is one of the reasons why engines and machinery are usually so heavy. As most experienced designers will tell you, any major requirement for torsional strength and stiffness in a structure is apt to be a curse and a blight. It puts up the weight and the expense and altogether provides a quite disproportionate amount of trouble and anxiety to the engineer. Nature does not seem to mind taking a lot of time and trouble, and she has no sense at all of the value of money, but she is intensely sensitive to metabolic cost, that is to say, to the price of a structure in terms of food and energy, and she is also generally pretty weight conscious. It is not surprising, therefore, that she seems to avoid torsion like poison. In fact, she nearly always manages to dodge out of any serious requirement for the provision of torsional strength or stiffness. As long as they are not subjected to unnatural loads, most animals can afford to be weak in torsion. None of us likes having our arm twisted, and in normal life the torsional loads on our legs are small. However, when we attach long levers called skis to our feet and then proceed to ski rather badly, it is only too easy to apply large twisting forces to our legs. Because this is the commonest cause of broken legs in skiing, it has led to the development of the modern safety binding, which releases automatically in torsion. Not only our legs, but virtually all bones, are surprisingly weak in torsion. Should you wish to kill a chicken, or any other bird, much the easiest way is to wring its neck. This is well known. What is less well known is how very weak are the vertebrae in torsion, as the beginner is apt to find out to his disgust and embarrassment when the head comes off in his hand. But then neck wringing, like ski ing, is an entirely artificial hazard and quite out of the ordinary course of nature. Unlike engineers, nature has little interest in rotary motion and, like the Africans, she has never bothered to invent the wheel. Note that there is a relationship between G and E for isotropic materials like metals, where Q equals Poisson's ratio. Warp threads or yarns are those which run parallel to the length of a roll of cloth. Weft threads are those which run across the cloth, at right angles to its length. An understanding of this principle is very important when making things like balloons and pneumatic dinghies from rubberized fabric. If shear distortions are incurred, the rubber coating is strained in such a way that the fabric will leak. The cuticles of many worms and other soft animals are strengthened by systems of helically disposed collagen fibers, Chapter 8. The worm has much the same problems as the dressmaker, though it is often more successful in solving them. It is difficult to put a crease into a worm. Note that, for an initially flat membrane to conform easily to a surface with pronounced two-dimensional curvature, it is necessary to have both a low Young's modulus and a low shear modulus. This is essentially the problem of map projection which was encountered by Mercator about 1560. Nor had many of the academic engineers. Even as late as 1936, the basic Lanchester-Prandtl, or vortex, theory of fluid dynamics was neither taught nor permitted to be used in the Department of Naval Architecture in the University of Glasgow. To those of a younger generation who may not be disposed to believe this story, I would point out that, A, I was myself a student in the department at the time, and, B, much the same sort of thing happens with modern theories of fracture mechanics, Chapter 5, in present-day engineering departments. This is why a dead leaf or a sheet of cardboard falls in the way it does. Chapter 13 The various ways of failing in compression. Or sandwiches, skulls and Dr. Euler. By reason of the frailty of our nature we cannot always stand upright. Collect for the fourth Sunday after Epiphany. As one would expect, the ways in which structures fail under compressive loads are rather different in their nature from the ways in which they break in tension. When we stress a solid in tension we are, of course, pulling its atoms and molecules further apart. As we do so, the interatomic bonds which hold the material together are stretched, but they can be safely stretched only to a limited extent. Beyond about 20% tensile strain, all chemical bonds become weaker and will eventually come unstuck. Although the actual details of the tensile fracture process are complicated, it is broadly true to say that, when a sufficient number of interatomic bonds have been stretched beyond their breaking point, the material itself will break. The same sort of thing is also true when a material is broken by shearing. Strictly speaking, however, there is normally no analogous case of interatomic bond failure, which is simply and directly due to compression. When a solid is compressed, its atoms and molecules are being pressed closer to each other, and under any ordinary conditions the repulsion between the atoms goes on increasing indefinitely as the compressive stress is raised. It is only when subjected to the enormous gravitational forces which exist in those stars which astronomers call dwarfs that the compressive resistance between atoms collapses, with nightmarish consequences. Nevertheless, lots of very ordinary earthly structures do break by what is commonly described as compression. What is really happening in failures of this sort is that the material or the structure finds some way of evading an unduly high compressive stress, usually by moving out from under the load, that is to say, by running away in a sideways direction, using one of the escape routes which are practically always available. Looked at from the energy point of view, the structure wants to get rid of an excess of compressive strain energy, and it will do so by means of whatever energy exchange mechanism happens to be practicable in the circumstances. Compression structures are thus apt to be rather shifty characters, and the study of compressive failure is more or less the study of ways of getting out of a tight place. As one might suppose, there are a number of different means of doing this. The escape method which the structure will use naturally depends upon its shape and proportions and upon the material from which it is made. We have already discussed masonry at some length. Although buildings are essentially compression structures, and masonry must be kept in compression all the time, yet they cannot be said to fail by compression at all. Paradoxically, they can only fail by getting into tension. When this happens, walls have a bad habit of developing hinge points, as a consequence of which they tip up and fall down. Although arches are rather more stable and responsible structures than walls, they are capable at times of producing 4 hinge points, after which they diminish both their strain energy and their potential energy by folding themselves up and reducing themselves to a heap of rubble. In any case, as we calculated in Chapter 9, the actual values of the compressive stresses in masonry are USUALLYVERYLOW, FARBELOWTHEOFFICIALCIOUSHNGSTERENGSTOFTHEMATERIAL. Crushing stresses, or the failure of short struts and columns in compression. However, if we take a brick or a block of concrete of fairly compact shape and subject it to a large compressive load, in a testing machine or by any other method, the material will eventually break in a manner which is conventionally called compression failure. Although brittle solids like stone, brick, concrete and glass are generally crushed in such a way that they are reduced to fragments, or sometimes to powder, the failure is still not, in the strict sense, a compressive one. The actual fracture nearly always takes place by shearing. As we said in the last chapter, both tensile and compressive stresses necessarily give rise to shears at 45 degrees. It is these diagonal shears which generally cause compressive failure in short struts. Figure 1. Typical compression failures for a brittle solid such as cement or glass. Fracture is really due to shearing. As we also said earlier on, all practical brittle solids are full of cracks and scratches and defects of one kind or another. Even if this is not the case when they are first made, such materials very soon become abraded from all sorts of virtually unavoidable causes. Naturally, these cracks and scratches point in all directions in the material. It follows that a fair number of them will always be found to lie in directions which are diagonal to an applied compressive stress, that is to say, more or less parallel to the resulting shear stress, figure 1. Like tensile cracks, these shear cracks have a critical Griffith length. In other words, a crack of a given length will propagate at a certain critical shear stress. When such conditions are reached in a brittle solid, such as concrete, the shear cracks will propagate suddenly, violently and perhaps explosively. When a shear crack has run diagonally across the width of a strut or other compression member, the two parts naturally slide past each other, so that the strut is no longer capable of carrying a compression load. The resulting collapse is likely to result in a large release of energy, and this is why brittle materials like glass and stone and concrete throw out splinters, which can be dangerous when they are crushed or hit with a hammer. In fact, the release of strain energy is quite often large enough to pay for reducing the material to a powder. This is what happens when we crush lumps of sugar with a hammer or a rolling pin. The failure of a ductile metal, or, come to that, of butter or plasticine, under compressive stress is due to similar causes. What happens is that the metal slips or slides, because of the dislocation mechanism, within itself under the shearing stress. Again, this happens along planes roughly at 45 degrees to the compressive load, thus a short metal strut bulges outwards into some barrel-like shape, figure 2. Because of the high work of fracture of ductile metals, such materials are far less likely to throw off splinters during compression failure, and the immediate consequences of the fracture are likely to be less dramatic and a good deal less dangerous. It is this effect, the tendency to bulge under compression, which we make use of when we spread the head of a metal rivet by hammering it or by squeezing it in a hydraulic press. Materials like wood and the artificial fibrous composites such as fiberglass and carbon fiber materials generally fail in compression in a rather different way. In such cases, the reinforcing fibers buckle or fold in sympathy with each other under the compressive load, so that what is called a compression crease runs across the material. These compression creases may run either diagonally or at 90 degrees to the direction of the applied compressive stress, or sometimes at various angles in between, figure 3. Unfortunately, compression creases often tend to form in fibrous materials at quite low stresses. These materials are therefore sometimes weak in compression, and this point needs to be considered when using them. Figure 2. Failure of a ductile material, such as a metal in compression. Failure is again due to shearing, but this time the effect is to cause the metal to bulge. Figure 3. Failure of a fibrous material such as wood or fiberglass in compression. Note that the 90 degrees crease involves a volume contraction and can therefore only take place in a material containing voids, such as wood. Solid composites must fail by mode B, which does not involve a change of volume. Breaking stresses of materials in tension and in compression. The various textbooks and reference books generally make a great parade of tabulating the tensile strengths of common engineering materials. As a rule, however, these books are a good deal more reticent about compressive strengths. This is partly because the experimental values of the compressive failing stresses of materials vary much more with the shape of the test piece which has been employed than do the tensile strengths. Sometimes this effect is so great that it becomes almost meaningless to quote a figure. However, although a cautious attitude to compression strengths is in some ways justified, it does have the effect of glossing over some of the facts of structural life. One of these facts is that there is really no consistent relationship at all between the tensile and the compressive strength of a material. Some rather approximate figures for common materials are given in Table 5. The compressive strength values are those which might be obtained using test pieces. Having a ratio of length to thickness of something like 3 or 4 to 1. For specimens much fatter or thinner than this, the breaking stresses might be quite different. One of the obvious lessons to be drawn from Table 5 is that, when we come to design a thing like a beam which is stressed in both tension and compression, we may need to watch our step. It may be necessary to design a beam which has a highly asymmetrical section. In Victorian cast iron beams, the tension side is usually very much thicker than the compression side, because cast iron is weaker in tension than in compression, Figure 4. Contrariwise, the wing spar of a wooden aircraft, such as a sailplane, is always much thicker on the upper or compression side, since wood is weaker in compression than in tension, Figure 5. Table 5. Some materials with unequal tensile and compression strengths. These figures are approximate. Tensile strength, compressive strength, material PSIMN M2 PSIM NIM2. Wood 15,100 4,027 cast iron 6,040 50,340 cast aluminium 6,040 40,270 zinc die castings 5,035 40,270 bakelite, polystyrene, and other brittle plastics 2015 8055. Concrete 600 for 6040. Figure 4. Cast iron beams are usually made thicker on the tension face than on the compression face, because cast iron is weaker in tension. Figure 5. A wooden glider wing spar is usually made thicker on the compression side than on the tension face because wood is weak in compression. The compressive strength of timber and of composite materials. He said he had been making masts for over 50 years, and, as far as he knew, they had all been sound spars. He said I was the only man he had ever met who deliberately planned to ruin a good mast by cutting the heart right out in a most sensitive spot. He said that any man who could do a thing like that would, and here I toned down his words a lot, curse aloud in church, wipe his nose on the tablecloth, take soundings in a cesspit and eat the arming. And that was that. Both George and I thought secretly that the spar was a great deal too whippy for comfort, but in the face of those experts we decided it might be wise to keep our opinions locked up within us. Which was well. For the experts were expert. Later on, when our main shrouds did carry away in a wicked Gulf Stream squall, that mast bent, and bent and bent, until it looked like the letter S, but it would not break. Western Martyr, the South Seaman. In real life, as soon as we start to deal with columns of any length, the distinction between a column and a beam becomes a good deal confused. A longish column, such as a leg bone of an animal, is nearly always subject to some degree of bending, and as a result the material on the concave side is compressed more than it is elsewhere. Contrariwise, in a beam or a truss, especially one of sophisticated design, the compression boom must be considered as a strut. In either case, if the material itself tends to be weak in compression, whether we call the structure a beam or a column, failure will generally begin when the total compressive stress at the worst place reaches a dangerous level. The best examples of columns which are also subject to bending are provided by trees and the masts of traditional sailing ships. Tree trunks have to sustain the weight of all the bits and pieces of the tree in direct compression, but, in practice, the stress is set up by bending forces caused by wind. Pressure are likely to be larger and more important. Again, masts are nominally struts, carrying only axial compression, but, because of the stretching of the rigging, and for other causes, they are in fact subject to a good deal of bending, especially if anything in the rigging should happen to break. The masts of big ships like HMS Victory had to be built up by joining many pieces of wood together with iron hoops, but for masts of more moderate size the traditional spar-makers preferred to use single pine or spruce trees, left as nearly as possible in their original condition. Not only did these craftsmen strongly resist any suggestion that a mast should be built up or hollowed out in such a way as to produce a more efficient tubular section, they also took care to remove as little as possible, beyond the bark of the outer surface of the tree. In other words, they tried, as far as they could, to use the tree in its natural state. For many years professional engineers, who knew all about beam theory and neutral axes and second moments of area, despised this as so much traditional nonsense. In fact, the first thing that a modern engineer does with a tree is to cut it up into small pieces, which he then glues together again, preferably into some kind of hollow section. It is only recently that we have realized that, after all, the tree does know a thing or two. Among other subtleties, the wood in various parts of the trunk grows in such a way that it is pre-stressed. Figure 6. A. Tree bent by the wind with no pre-stress in wood. Stress distribution across the trunk is linear and maximum tension and compression stresses are equal. B. Pre-stressed tree in a calm. The outside of the trunk is in tension all round, the inside is in compression. C. Pre-stressed tree in a strong wind. Compression stress is halved and this tree can bend twice as far as the one in A. Now in a beam such as a glider wing spar, where the biggest bending load is practically always in one direction, it is possible, though not very efficient, to make the compression boom of the spar thicker than the tension boom to allow for the fact that wood is much weaker in compression than it is in tension. Things like trees and masts, however, may have to resist bending forces coming from many different directions, according to the caprices of the wind, and so this solution is not open to them. Trees, at any rate, have to have a symmetrical cross-section, usually around 1. For a UN pre-stressed section the distribution of stress under bending loads will be linear, as in Figure 6a. For such an arrangement, when the compressive stress reaches about 4,000 psi, 27 mm2, the beam, that is the tree, will start to break. This is where the pre-stressing comes in. Somehow or other the tree manages to grow in such a way that the outer wood is normally in tension, to the extent of something over 2000 psi or 14 mm2, while the middle of the tree, by way of compensation, is in compression. Thus the distribution of stress across the trunk, under normal conditions, is something like Figure 6b. One of the important consequences of Hookean elasticity is that we can safely and truthfully superpose one stress system upon another. Thus, when we add Figure 6a to 6b we get Figure 6c. By this method the tree roughly halves the maximum compressive stress, for 1000 psi, 2000 psi equals 2000 psi, and so doubles its effective bending strength. It is true that the maximum tensile stress has been raised, but the wood has plenty in hand in this respect. What the tree does in the way of protecting itself by pre-stressing is exactly the opposite of what we do when we make a pre-stressed concrete beam. In the latter case the concrete is weak in tension and relatively strong in compression. The danger is that, when the beam is bent, failure may occur in the concrete on the tension face. To avoid this we put the steel reinforcing rods, which are inside the beam, permanently into tension, so that the concrete is permanently in compression. Thus the beam has to be bent considerably before the compressive stress in the concrete near the surface is relieved and replaced by a tension stress. Thus the cracking of the cement is postponed, since the beam has to be bent further before the critical tensile strain is reached. As we have said, both timber and the fibrous composite materials generally fail in compression by the formation of bands or creases of bent and buckled fibers. My colleague Dr. Richard Chaplin points out that these compression creases have a good deal in common with cracks which occur in tension. In particular, they are often started by stress concentrations at holes or other defects in the material. In general, fastenings like nails and screws do not much weaken timber, always provided that they are in place and fit tightly. Once they are removed, however, the resulting hole has a much more serious effect, and no doubt the same is true of knots in timber. In a highly stressed wooden structure, such as a glider or a yacht's mast, it is therefore wise to leave unwanted nails and screws alone and not try to pull them out. If needs be, they can be cut off flush with the surface of the wood. Furthermore, as Richard Chaplin says, the formation of compression creases in a fibrous material requires energy. In fact, the amount of energy required is rather larger than the work of fracture of the material in tension. It follows that the propagation of compression creases needs a supply of strain energy and that their behavior is something like that of a Griffith crack. There are, however, some important differences. We have said that, in materials of the kind we have been discussing, compression creases can occur both at 45 degrees and also at 90 degrees to the direction of loading. They can also occur at other angles, between 45 degrees and 90 degrees. The 45 degrees crease is effectively a shear crack, and, if the conditions are right, it will spread right across the material, much like a Griffith crack in shear. However, the 90 degrees crease is shorter, and therefore consumes less energy, for a given depth of penetration below the surface of the material. For this reason the 90 degrees crease is, on the whole, more likely to occur. However, although the 90 degrees crease seems to be easier to start off, it is more likely to come to a halt after traveling for a short distance. This is because, as the crease advances, its two sides tend to get pinched together, or come up solid, and so cease to release much strain energy. Thus complete failure is unlikely to take place, at any rate immediately. What may happen in these circumstances is that many little creases will form, one behind the other, all along the compression surface of a beam. This can be seen on the compression face of a wooden bow, and sometimes with oars, figure 7. Although engineers often advocate efficient H sections or box sections for beams, this can be a mistake. For reasons which are easily demonstrated, the strain energy release conditions are often less favorable to the propagation of both cracks or compression creases when the beam section is rounded, like a tree, and this is probably the rationale behind the rounded cross-sections of most wooden bows. No doubt something of the kind is also relevant to the rounded cross-sections of the bones of animals. Figure 7. Multiple compression creases on the compression face of a round piece of timber such as a tree, a mast, an oar or a bow. These creases may not be able to spread, and so complete fracture does not occur. So long as the material is stressed consistently in compression, there are many hindrances to the spread of compression creases. This is one of the reasons why wood is generally such a safe material. However, under conditions of reversed loading, it can be very dangerous indeed. This is because the buckled fibers which constitute a compression crease have little or no tensile strength, and so, under tension forces, the crease acts like an ordinary crack. It is especially dangerous because, in tension, there is now no restriction on the release of strain energy since the two sides of the crack are free to spring apart. One of the best ways to arrange for a wing to come off a wooden glider in flight is to make a heavy landing with it. If one puts the aircraft down with a really bad bump, the wings will, momentarily, be bent downwards towards the ground. This may cause compression creases in the would have what is normally the tension part of the main spar. If this happens, the creases are most unlikely to be spotted during routine inspections. The next time the glider is flown, the spar may break in tension at this point, after which, of course, the wing will fall off. See Figure 9. Leonard Euler and the buckling of thin struts and panels. What we have said so far applies to struts and other compression members which are fairly short and thick. As we have seen, these usually fail in compression by a diagonal shearing mechanism, or sometimes by the formation of local creases in the fibers. However, a large number of compression structures of one sort or another involve members which are long and thin and which fail in a totally different way. A long rod, or a membrane such as a thin sheet of metal or a page of this book, fails in compression by buckling, as can very easily be seen by doing the simplest experiment. Take a sheet of paper and try to compress it lengthwise. This mode of failure, which has important technical and economic consequences, is called Euler * buckling, since it was originally analyzed by Leonard Euler, 1707–83. Euler came from a German-Swiss family well known for its mathematical ability, and he very soon acquired fame as a mathematician, so much so that, while still quite young, he was invited to Russia by the Empress Elizabeth. He spent most of his life at the court of St. Petersburg, taking refuge for a time with Frederick the Great at Potsdam when the political situation in Russia got too exciting. Life at the courts of the enlightened despots in the middle of the 18th century must have been both interesting and colorful, but little of this is reflected in Euler's voluminous writings. As far as I can trace, there appears to be no incident of any noticeable human interest recorded of him in any of his biographies. He simply went on for a very long time doing mathematics and writing it all down in an enormous number of learned papers, the last of which was still being published 40 years after his death. As a matter of fact, Euler did not really mean to do anything about columns at all. What happened was that, among a great many other mathematical discoveries, he had invented something called the calculus of variations, and he was looking for a problem to try it out on. A friend suggested that he might use this method to calculate the height of a thin vertical pole which would just buckle under its own weight. It was necessary to make use of the calculus of variations to tackle this rather hypothetical problem because, as we mentioned in Chapter 3, the concepts of stress and strain were not invented until much later. Put in modern terms, what Euler came up with was what we now call the Euler formula for the buckling load of a strut, which is where P equals load at which the column or panel will buckle, E equals Young's modulus of the material, I equals second moment of area, the so-called moment of inertia, of the cross-section of the strut or panel, Chapter 11, L equals length of strut. Naturally, all these quantities must be in mutually consistent units. It is curious, but convenient, that so many of these important structural formulae should be, algebraically, so very simple. Euler's formula applies to all sorts and kinds of long, thin columns and struts, both solid and hollow, and, perhaps even more importantly, to thin panels and plates and membranes such as occur in aircraft and ships and motor cars. Thus, if we plot the failing load of a strut or a panel against its length, we get a diagram something like Figure 8, which shows two regimes of failure. For a short strut, failure will be by crushing. When the ratio of length to thickness increases to a value between about 5 and 10, then this line will be crossed by the curve which represents Euler buckling failure. Buckling now becomes the weaker mode, and so long struts will fail in this way. In practice, the changeover from crushing failure to Euler buckling is not a sharp one, and there will be a transitional region, something like the dotted line in the diagram. Figure 8. Variation in the compressive strength of a column with its length. The form of the Euler formula which has just been given assumes that the strut or panel is pin-jointed, or free to hinge, at both ends, Figure 9. Usually, anything which tends to prevent a strut or panel from hinging at the ends will increase the buckling load. For the extreme case, where both ends are rigidly restrained, the buckling load, P, is multiplied by as much as 4. Very frequently, however, the achievement of any considerable degree of end restraint involves extra weight and complication and cost and may not be worth doing. Furthermore, rigid end connections will transmit any misalignment of the end attachments to the strut. If this happens, the strut may be prematurely bent, and so, in practice, made weaker. For this reason, the rigid stepping of masts, by attaching them both to the deck and the keel, is no longer usual. Figure 10. Figure 9. Various Euler conditions. A. Both ends pin-jointed. B. Both ends fixed in direction and position. C. One end in caster, the other pin-jointed and free to move sideways. It will be noticed that, in the Euler formula which we have just written down, there is no term which represents a braking stress. The buckling load of a strut or a panel of a given length depends solely upon the four/, or second moment of area, of the cross-section and upon the Young's modulus or stiffness of its material. A long strut does not break when it buckles. It just bends elastically in such a manner as to get out of the way of the load. If the elastic limit of the material has not been exceeded during buckling, then, when the load is removed, the strut will simply spring straight again and recover its original shape, quite undismayed by its experience. This characteristic can often be a good thing, for it is possible to design unbreakable structures in this way. Broadly speaking, this is how carpets and doormats work. Predictably, nature uses the principle very widely, especially for small plants like grasses which inevitably get trodden on. This is why it is possible to walk on a lawn without doing it any harm. It is the ingenious combination of spiky thorns with Dr. Euler's principle which makes a quickset hedge practically indestructible and impenetrable to both men and cattle. On the other hand, mosquitoes and other insects which make use of long slender stabbing weapons have to employ an indecent amount of low structural cunning to prevent these thin struts from buckling when they sting you. Figure 10. If a column is clamped at the ends in such a way as to force it out of alignment, its buckling load may be reduced. Since rigging is liable to stretch, it is no longer customary to fix masts at both deck and keel. During Euler's lifetime, the actual technological uses for his formula were very few. Practically the only important application would have been in the design of ships' masts and other spars. However, contemporary shipwrights had already got this problem under control in a pragmatic way. The magnificent 18th-century textbooks on shipbuilding, such as Steele's Elements of Mast-Making, Sail-Making, and Rigging, contain extensive tables of the dimensions of every kind of spar, based on experience, and it is doubtful if these recommendations could have been much improved upon by calculation. Serious interest in buckling phenomena only began about a century after Euler's time and was largely due to the increasing use of wrought iron plates in constructional work. These plates were naturally much thinner than the masonry and woodwork to which engineers had been accustomed. The problem was first tackled seriously in the case of the Menai Railway Bridge, about 1848. The design of this bridge was the joint responsibility of three great men: Robert Stephenson, 1803–59; Eaton Hodgkinson, 1789–1861, a mathematician and one of the first professors of engineering, and Sir William Fairbairn, 1789–1874, a pioneer in the structural use of wrought iron plates. Stephenson's railway suspension bridges had been a failure because they were too flexible. Furthermore, the Admiralty, not unreasonably, insisted upon a clear 100 feet, 30 meters, headroom beneath the bridge for shipping. The only way of combining the necessary stiffness with the headroom which was demanded seemed to be to design a beam bridge far longer than had ever been built before. For various reasons it seemed best to make the beams, each of which had to be 460 feet, 140 meters, long, in the form of tubes built up from wrought iron plates, with the trains running inside the tubes. It fairly soon became evident that one of the most serious design problems lay in the buckling of the iron plates which formed the upper or compression side of the beams. Although Euler's formula is accurate enough for simple panels and struts, the shape of the bridge tubes was necessarily complicated, and no adequate mathematical theory existed at that time. The three designers had thus no option but to experiment with models. As might have been expected, these proved to be confusing and unreliable, so much so that the three men quarreled among themselves, and at one time it looked as if the partnership would break up with no really safe design for the tubes in sight. Eventually, however, a cellular box beam was decided upon, figure 11. To everybody's immense relief this proved satisfactory, and it is there to this day. Figure 11. Britannia Bridge, tubular box beam. Since Stephenson's time, a very great amount of mathematical research has been carried out on the buckling of thin shells, but the design of such structures is still accompanied by even more than the usual degree of uncertainty. So the development of critical structures of this kind is likely to be expensive, because of the full-scale strength tests which may be needed before the design can be finalized. Tubes, ships and bamboos, and something about brazier buckling. Since, according to Euler, the buckling load of a strut varies as EIL2, the compressive strength of a long column is liable to be very low indeed. The only thing we can do about this is to increase EI if possible in proportion to L2. For most materials the Young's modulus of elasticity, is pretty well constant, so what we have to do in practice is to increase I, the second moment of area of the cross-section. This means that we have got to make the column fatter. That, of course, is exactly what we do in masonry, for instance in the sturdy columns of a Doric temple. The result, however, is excessively heavy, and if we want to make a light structure then we shall have to design some sort of expanded section. This sometimes takes the form of an H or star shape, or sometimes a square box. On the whole, however, round tubes are usually better and more efficient. Figure 12. Brazier or local buckling of a thin-walled tube under axial compression. The use of tubes is extremely popular both with engineers and with nature, and tubular struts are very widely used for all sorts of purposes. However, a tube under compression has a choice of two modes of buckling. It may buckle in the way we have been describing, that is to say, in a long wave mode, over its whole length, Euler fashion. Alternatively, it may buckle in a short wave mode, that is to say, locally, by putting a sort of crease or crumple into the wall of the tube. If the radius of the tube is large and if the wall is thin, then the strut may well be safe against Euler, or long wave, buckling, but it will fail by the local crumpling of the skin. This is easily demonstrated with a thin-walled paper tube. One form of this local buckling or crumpling is called brazier buckling, figure 12. It is this effect which sets a limit to the use of simple tubes and thin-walled cylinders in compression. The commonest way to guard against brazier buckling is to stiffen the skin of a thin-walled structure by attaching extra members, such as ribs or stringers, to it. Stiffeners which run circumferentially are generally called ribs, while those which run lengthwise are called stringers, except by botanists, who will call them ribs. The shell plating of ships is traditionally stiffened by means of ribs and bulkheads, though, recently, large tankers have been built on the Shearwood system, which largely depends upon longitudinal stringers. A sophisticated shell structure, such as an aircraft fuselage, is usually stiffened by both ribs and stringers. The hollow stems of grasses and bamboos, which tend to flatten when they are bent, are very elegantly stiffened by means of nodes or partitions or bulkheads, spaced at intervals along the stem, figures 13 and 14. Figure 13. Two ways of stiffening a hollow plant stem against local buckling. A. Longitudinal stringers. B. Nodes or bulkheads, common in grasses and bamboos. Figure 14. Engineering shell structures such as ships and aircraft generally use both stringers and ribs. O. Bulkheads, THISADIAGRAMOFTHIOUSCTIONOFTENUSEDINOILTANKERS. Leaves, sandwiches, and honeycombs. Thin plates and panels and shells are continually cropping up both in nature and in technology, and, the larger and the thinner these structures are, the more likely they are to deflect or crumple under bending and compressive loads. In principle, anything which stiffens a column or a panel in bending will also increase its resistance to buckling and so make it stronger in compression. One way of doing this is by staying a strut or a panel with ropes or wires. This is a solution which is never used in plants. Alternatively, and perhaps preferably, one can stiffen the member with ribs or stringers, by corrugating it, or by making it of cellular construction. Wood is a cellular material, and so are most other plant tissues, notably the stem walls of grasses and bamboos. Furthermore, in the competitive struggle for existence, many plants depend critically upon the structural efficiency of their leaves, because they must try to expose the maximum area to sunlight, for photosynthesis, at the minimum metabolic cost. Leaves are therefore important panel structures, and they seem to make use of most of the known structural devices to increase their stiffness in bending. Nearly all leaves are provided with an elaborate rib structure *. The membranes between the ribs are stiffened by being of cellular construction, and in some cases they are further stiffened by corrugations. In addition to all this, the leaf as a whole is stiffened hydrostatically by the osmotic pressure of the sap. In engineering structures, panels and shells are very often stiffened by means of ribs or stringers which are glued or riveted or welded to the plating, though this is not always the lightest or the cheapest way of doing the job. Another way of tackling the problem is to make the shell plating in two separate layers which are then spaced apart by being glued to some kind of continuous support, usually made as light as possible. Arrangements of this kind are called sandwich constructions. In modern times, sandwich panels were first used for serious constructional purposes by Mr. Edward Bishop, de Havilland's famous chief designer, for the fuselage of the now-forgotten Comet aircraft of the 193 OS. It is probably best known for its use in the successor to this aeroplane, the wartime Mosquito. In both these aircraft the core of the sandwich was made of lightweight balsa wood, with skins of heavier and stronger birch plywood glued to either side. Though the Mosquito was a most successful aircraft, balsa wood is apt to soak up water and rot. Moreover, supplies of this rather soft and fragile tropical wood are limited in quantity and variable in quality. As things turned out, research on core materials for sandwich shells and panels was much stimulated at about this time by another factor altogether. This was the introduction of airborne radar. With this equipment, the moving radar reflector or scanner had to be housed and protected by putting it inside a large streamlined dome or fairing, which soon came to be known as a radome. Naturally, these fairings had to be transparent to high-frequency radio waves, and this meant that, in practice, they had to be made from some sort of plastic, usually fiberglass or perspex. The transparency of the radome shell to radar could be much improved, at least in theory, by the use of a sandwich construction whose thickness was carefully related to the wavelength of the radiation which was being transmitted, in exactly the same way as the thickness of the coating or blooming on a modern camera lens is related to the wavelength of visible light. Damp balsa, like any other damp wood, is nearly opaque to radar, and under wartime conditions balsa is practically always damp. This ruled out its use for radomes, and so it was necessary to develop more waterproof lightweight materials. This was done by foaming artificial resins of various kinds. The result looked something like a meringue or aero chocolate, figure 15. A good many foamed resins of this kind were developed. They have a number of virtues, and they were used not only for the cause of radome sandwiches but for all sorts of other structural sandwich panels as well. Some of them are still in use today. They are used, for instance, in boat building because the walls of their cells or cavities are nearly impervious to water. However, for the cause of sandwich panels of the highest structural efficiency, resin foams are rather heavier and rather less stiff than one might wish. In other words, the market for lightweight core materials was more or less an open one. Figure 15. Foamed resins are often used as lightweight core materials in sandwich constructions. One day, towards the end of 1943, a circus proprietor called George May called to see me at Farnborough. After he had told me several Gerald Durrell-type stories about the difficulties of keeping monkeys in traveling circuses, he produced something which looked like a cross between a book and a concertina. When he pulled on the ends of this invention, the whole thing opened out like one of those colored paper festoons which people use for Christmas decorations. It was in fact a sort of paper honeycomb of very lightweight but of quite surprising strength and stiffness. Did I think that such a thing could be of any use in aircraft? The snag, as George May modestly admitted, was that, since it was only made from brown paper and ordinary gum, it had no moisture resistance at all and would fall to bits if it got wet. This must have been one of the relatively few occasions in history when a group of aircraft engineers have been seriously tempted to throw their collective arms around the neck of a circus proprietor and kiss him. However, we resisted the temptation and told May that there could be no serious difficulty in waterproofing the paper honeycomb by means of a synthetic resin. This was exactly what we did. Figure 16. The paper from which the honeycomb was to be made was impregnated before use with a solution of uncued phenolic resin. After the honeycomb had been made and expanded, the resin was cured and hardened by baking it in an oven. As a result, the paper was not only made waterproof but also strengthened and stiffened. This material was very successful and was used in the cause of sandwiches for all kinds of military purposes. Though it is not used a great deal in aircraft nowadays, something like half the household doors in the world are made by gluing thin sheets of plywood or plastic on either side of a paper honeycomb. It is even more widely used abroad, especially in America, than in England, and the world production of paper honeycomb must be very considerable. Figure 16. Construction and use of paper honeycomb. A. Resin-impregnated paper is printed with parallel stripes of glue. B. Many sheets are glued together into a thick block with glue stripes staggered. C. When the glue is set, the block of material is expanded into a honeycomb. After this the resin is hardened. D. Slabs of honeycomb are glued between sheets of ply, plastic or metal to form a structural sandwich. Although the use of sandwich construction, foamed resin cores and honeycombs is relatively new in engineering, it has been used for a very long time in biology. What is called cancellous bone, figure 17, exploits this principle. Each of us carries around quite a good example in the bones of our skulls, which are, of course, subject to bending and buckling loads. Figure 17. Cancellous bone. Asterisk. The result may be a concentration of mass so dense that its own gravitational field is strong enough to prevent, not only the escape of any matter but also the departure of all forms of radiation. Thus no two-way communication is possible with such an area, and these regions of the universe are forever barred to us. These localities are known as black holes. Like the island in Sir James Barrie's eerie play Mary Rose, they like to be visited, but nothing can ever return. Asterisk. In so far as failure in both tension and compression tend to occur by shearing, as in ductile metals, the tensile and compressive strengths would be identical. However, there are so many exceptions to this rule as to make it practically valueless. Asterisk. Note that many seaweeds, which are made largely from alginic acid, a weak and brittle substance, are pre-stressed in the same sense as reinforced concrete. Just as reinforced concrete economizes in steel, so seaweeds economize in the scarce, strong component, cellulose. Asterisk as a crack or a compression crease with a straight front, like a saw cut, penetrates across a round section, its surface area may increase more rapidly than the rate of release of strain energy from the material behind it, and so Griffith is frustrated. Asterisk pronounced Euler. Asterisk except, of course, his increasing blindness in later life. Asterisk several modern proofs of Euler's formula are to be found in the textbooks. See, for instance, The Mechanical Properties of Matter by Sir Alan Cottrell. Asterisk in a thin-walled circular tube, local buckling will generally occur when the stress in the skin reaches a value equivalent to where it equals wall thickness A equals radius of tube E equals Young's modulus. Asterisk the ribs of the leaf of the Victoria Regia lily are traditionally supposed to have inspired Sir Joseph Paxton's design for the Crystal Palace in 1851, which had no direct connection with the later jet airliner of the same name. Part 4. And the consequence was. Chapter 14 The Philosophy of Design. Or the shape, the weight, and the cost. Philosophy is nothing but discretion. John Selden, 1584–1654. As we have seen, very much the commonest day-to-day practical use of structural theory is in analyzing the behavior of some specific structure, either one which it is proposed to build, one which is actually in existence but whose safety is in question, or else one which has, rather embarrassingly, already collapsed. In other words, if we know the dimensions of a given structure and the properties of the materials from which it is made, we can at least try to predict how strong it ought to be and how much it will deflect. However, although calculations of this sort are clearly very useful in particular instances, this kind of approach is only of limited help to us when we want to understand why things are the shape they are, or when we want to choose which, out of several different classes of structure, would be best for a particular service. For instance, in making an aeroplane or a bridge, would it be better to use a continuous shell structure made from plates or panels, or else a criss-cross lattice arrangement built up from rods or tubes and braced, perhaps, with wires? Again, why do we have so many muscles and tendons and comparatively few bones? Furthermore, how is the engineer ever to select from the large variety of materials which are usually available? Should he make his structure from steel or aluminium, from plastic or from wood? The design of plants and animals and of the traditional artifacts did not just happen. As a rule, both the shape and the materials of any structure which has evolved over a long period of time in a competitive world represent an optimization with regard to the loads which it has to carry and to the financial or the metabolic cost. We should like to achieve this sort of optimization in modern technology, but we are not always very good at it. It is not widely realized that this subject, which is sometimes called the philosophy of design, can be studied in a scientific way. This is a pity, because the results are important, both in biology and in engineering. Although not much regarded, the study of the philosophy of design has, in fact, been going on for quite a number of years. The first serious engineering approach to the subject was made by G.M. Michel around 1900. Though biologists had been making remarks about the square cube law, Chapter 9, practically since it was propounded by Galileo, it was not until 1917 that Sir Darcy Thompson published his beautiful book on growth and form, still in print, which was the first general account of the influence of structural requirements on the shapes of plants and animals. For all its many virtues, the book is not a very numerate one, and the engineering views expressed are not always sound. Though greatly, and justly, praised, growth and form did not have much real influence on biological thinking, either in its own time or for long afterwards. It does not seem to have influenced engineers very much either, no doubt because the time for an interaction between biological and engineering thought was not ripe. In recent years, the chief exponent of the mathematical study of the philosophy of structures has been H. L. Cox. Besides being a distinguished elastician, Mr. Cox has the additional merit of being an expert on Beatrix Potter. I hope that he will forgive me for saying that he is in some ways a little like the great Thomas Young. For he shares not only something of Young's genius, but also a good deal of Young's obscurity of presentation. I am afraid lesser mortals often find Cox's expositions difficult to follow without the aid of an evangelist or interpreter. This may account for the fact that his work has received less attention than it deserves. Much of what follows is based on Cox, directly or indirectly. Let us begin with his analysis of tension structures. The design of tension structures. It is a curiosity of engineering design that it is impossible to fashion a simple tension member without first devising some end fitting through which the load may be applied, and whether the material be wrought iron or liana, wire rope or string, the stress system in the end fitting is a great deal more complicated than simple tension. There is plenty of scope for theory in the design of tension end fittings, but there is also a great deal of experience, and whether the competition is from the ancient pygmies' mastery of the craft of making knots in lianas, or from Brunei's development of efficient eye-bars, experience will often dictate the design. Still, the theorist has the final word. H. L. Cox, The Design of Structures of Least Weight, Pergamon, 1965. If we did not have to consider the effect of end fittings, the philosophy of tension structures would be very simple indeed. For one thing, the weight of a tension structure, fitted to carry a given load, would be proportional to its length. That is to say, a rope strong enough to carry a load of 1 ton over a distance of 100 meters would weigh just 100 times as much as a rope safe to carry the same load over 1 meter. Furthermore, provided that the load were evenly shared, it would make no difference whether a given load was supported by one single rope or tie bar, or by 2 ropes or bars each having half the cross-section. This simple view is upset by the necessity for end fittings, that is to say, by the need to get the load in at one end of the member and out at the other. Even an ordinary rope will need a knot or a splice at each end. The knot or splice will be relatively heavy and may cost money. If we are to do an honest reckoning, this weight and cost will have to be added to that of the bare tension member itself. The weight and the cost of the end fittings will be just the same, for a given load, whether the rope be long or short. Thus, other things being equal, the weight and cost of a tension member per unit length will be less for a long member than for a short one. In other words, the weight is not directly proportional to the length. Again, it can be shown, from the algebra and geometry of such a system, that the total weight of the end fittings of 2 tension bars, operating in parallel, is less than that of the end fittings of a single rope or bar of equivalent cross-section. It follows that, in general, weight is saved by subdividing a tensile load between 2 or more tension members instead of carrying it in a single one. As Cox points out, the stress distribution in end fittings is always complex and must include more or less severe stress concentrations, from which cracks will spread if they get the chance. Thus both the weight and the cost of the fittings will depend both upon the skill of the designer and also upon the toughness, that is to say, the work of fracture, of the material. The higher the work of fracture, the lighter and the cheaper the fitting will be. However, as we saw in Chapter 5, toughness is likely to diminish as tensile strength increases. In the case of common engineering metals, like steel, the work of fracture falls dramatically with increase of tensile strength. Thus, in choosing a material for a tension member, we are commonly faced with incompatible requirements. To reduce the weight of the middle or parallel part of a tie bar, we should like to use a material of high tensile strength. For the end fittings, we generally want a tough material, which is only too likely to imply the acceptance of a low tensile strength. Like many difficulties, this one must be solved by a compromise, which in this case depends chiefly on the length of the member. For very long members, such as the wire cables of a modern suspension bridge, it will generally pay to choose a high tensile steel, even if we have to accept extra weight and complication in connection with the end fittings at the anchorages of the cables. After all, There are only two of these, one at each end of the bridge, while there is perhaps a mile of wire in between. Thus the saving of weight over the middle part will more than compensate for any losses at the ends. But when we come to things like chains with shortish links, the situation is totally different. In each short link the weight of the end fittings may well be greater than that of the middle part and must be carefully considered. This is the case with the supporting chains of the older suspension bridges. Such things were generally made from a tough and ductile wrought iron of quite low tensile strength. As we said in Chapter 10, the tensile stress in the plate links of Telford's Menai bridge chains is less than a tenth of that in the wires of a modern suspension bridge, for this excellent reason. Very similar arguments apply to shell structures such as ships and tanks and boilers and girders which are fabricated from comparatively small plates of iron or steel. It also applies to riveted aluminium structures, such as conventional aircraft. All these may be considered more or less as two-dimensional chains with rather small links. In such cases it pays to use a weaker but more ductile material, otherwise the weight of the joints would be prohibitive. See Chapter 5, Figure 13, and p. 106. The multiplication of ropes and wires in ships and biplanes and tents generally results in a saving, rather than an increase, of weight. Naturally, all this cat's cradle business incurs the penalty of high wind resistance, high maintenance costs and general complication. This is the price we may have to pay for low structure weight. A similar principle can be seen in animals, where nature does not hesitate to multiply tension members such as muscles and tendons. Indeed, she adopts the same device as the Elizabethan seamen to reduce the weight of end attachments. The ends of many tendons are splayed out into a fan-shaped contrivance which Sir Francis Drake would have called a crow's foot. Each branch of the tendon has a separate little joint to the bone. Thus the weight, and perhaps the metabolic cost, is minimized. The relative weights of tension and compression structures. As we saw in the last chapter, the breaking stresses in tension and in compression for a given solid are often different, but for many common materials, such as steel, the difference is not very great, and so the weights of short tension and compression members are likely to be fairly similar. In fact, because a compression member may not need to have heavy end fittings, whereas a tension member does, a short compression strut may well be lighter, for comparable conditions, than a tension bar. However, as a strut gets longer, Dr. Euler begins to make himself felt. It will be remembered that the buckling load of a long column varies as LL2, where L is the length, and this implies that, for a rod of constant cross-section, the compressive strength diminishes very rapidly with increase of length. Thus, to support any given load, a long strut has to be made very much thicker, and therefore heavier, than a short one. As we said in the last section, the same consideration does not apply to tension members. It is revealing to study the problem of carrying 1 ton, 1,000 kilograms or 10,000 newtons, over a distance of 10 meters, 33 feet, first in tension and then in compression. In tension. For a steel rod or a cable we might allow a working stress of, say, 330 Nm2 or 50,000 psi in tension. Taking into account the end fittings, the total weight comes out at about 3 to 5 kilograms or about 8 pounds. In compression. To try to carry such a load in compression over such a distance by means of a solid steel rod would be silly, because if a solid rod were thick enough to avoid buckling it would need to be very heavy indeed. In practice we might well use a steel tube, which would have to be about 16 centimeters 6 inches in diameter with a wall thickness of, say, 5 millimeters 0 to 2 inch. Such a tube would weigh 200 kilograms or about 450 pounds. In other words, it would weigh between 50 and 60 times as much as the tension rod. The cost might well be in the same proportion. Furthermore, if we should want to subdivide a compression structure, the situation gets not better but much worse. If we want to support a load of 1 ton, not by a single strut, but by some table-like arrangement of 4 struts, each 10 meters long, then the total weight of the struts would be twice as great, that is to say, 400 kilograms. Or 900 pounds. The weight goes on increasing the more the structure is subdivided, in fact to square root n where n is the number of columns. See Appendix 4. On the other hand, if we increase the load, keeping the distance the same, then the weight of a compression structure becomes relatively better. For instance, if we increase the load 100-fold, that is, from 1 ton to 100 tons, then, though the weight of a tension member has gone up at least in proportion from 3 to 5 kilograms to 350 kilograms, yet the weight of a single strut to carry this load over 10 meters increases only tenfold, that is, from about 200 kilograms to about 2,000 kilograms. So, in compression, it is proportionately very much more economical to support a heavy load than a light one, Figure 1. All these considerations operate in the same sort of way for panels and shells and plates and membranes as for simple struts and poles and columns, Appendix 4. Figure 1. Diagram illustrating the relative weight cost of carrying a given load over a distance L. Considerations of this kind provide the rationale of things like tents and sailing ships. With such devices it pays, hands down, to collect the compression loads into a small number of masts or poles, contrived to be as short as possible. At the same time the tension loads, as we have said, are better diffused into as many strings and membranes as may be. Thus a bell tent, which has a single pole but many guy ropes, is likely to be the lightest building which can be made in proportion to its volume. However, almost any tent will generally be lighter and cheaper than a solid building made from timber or masonry. In the same way, a cutter or a sloop, which has a single mast, is a lighter and more efficient rig than a ketch or a schooner or any other more complicated arrangement with several masts. This is also the reason why the A-shaped or tripod masts used by the ancient Egyptians and by the designers of Victorian ironclads, Chapter 11, were heavy and inefficient. Again, the typical vertebrate animal, such as man, is on the whole a good deal like a bell tent or a sailing ship. There is a small number of compression members, that is, bones, more or less in the middle, and these are surrounded by a wilderness of muscles and tendons and membranes, even more complicated than the ropes and sails of a full-rigged ship, which carry the tensions. Furthermore, from the structural point of view 2 legs are better than 4, and the centipede is perhaps only saved from total inadequacy by the fact that its legs are so short. Scale effects, or second thoughts on the square cube law. It will be remembered that, long ago, it occurred to Galileo that, whereas the weight of a structure increased as the cube of its dimensions, the cross-sectional area of its load-carrying members increased only as the square, and so the stress in the material of geometrically similar structures ought to increase in direct proportion to the dimensions. Thus a structure which is liable to fail by tensile fracture induced, directly or indirectly, by its own weight must be made of thicker and stockier proportions the larger it becomes. In fact, its members would have to be made disproportionately thicker and heavier than the simple rule would indicate, because there is a sort of compound interest effect. Thus the size of all structures might be expected to be quite strictly limited. This square cube law has been bandied about by both biologists and engineers for a long time. Herbert Spencer and, later, Darcy Thompson said that it limited the size of animals, such as elephants, and engineers used to explain that it rendered impracticable the building of ships or aircraft appreciably larger than those already in existence. In spite of this, both ships and aircraft continue to get bigger and bigger. As a matter of fact, the square cube law seems to apply with full force only to the lintels of Greek temples, which are made from weak, heavy stone, icebergs and ice floes, which are made from weak, heavy ice, and things like jellies and blancmanges. As we have seen, in many sophisticated structures the weight of the compression members is likely to be many times greater than that of the tension parts. Since the compression members are likely to fail by buckling, they will become more efficient the larger the load they are called upon to bear, that is to say, the larger the structure is made. For this reason, although there is a disproportionate increase of weight with increase of size, the penalty is very much smaller than is implied by the square cube law. In practice, this penalty may be more than offset by various economies of scale. For instance, in a ship or a fish, an aircraft or a bird, the resistance to motion will be nearly in the ratio of the surface area, and this area will diminish, proportionately to the weight, as the size increases. It was Brunei's perception of this which impelled him to design the Great Eastern. Brunei's perception was right, though his great ship was a failure, and this is why we build enormous ships, such as supertankers, today. Furthermore, as we saw in Chapter 5, the size of large animals is more likely to be limited by considerations related to the critical Griffith crack length in their bones than by the square cube law. Space frames versus monocoques. Quite frequently the engineer is faced with a choice between a lattice structure built up, meccano fashion, from separate struts and tension rods, which is called a space frame, and a shell structure in which the load is carried in more or less continuous panels. This is called a monocoque. Sometimes the distinction between the two forms of construction is obscured by the fact that space frames are covered over with some sort of continuous cladding which does not really carry much load. This is the case with traditional timbered cottages, with modern steel-framed sheds and barns, which are covered with corrugated iron, and, of course, with animals which are covered with shells or scales. Sometimes the decision about which form to use is dictated by requirements which are not strictly structural. Thus an electricity pylon offers least wind resistance and least area of steel to paint when it is in the form of an open trellis or lattice tower. Again, it is generally more convenient to make a water tank, for instance, from a shell of thickish steel plates than in the form of a trellis supporting a watertight bag or membrane, even though the latter form may be lighter and is, in fact, the solution usually adopted by nature for stomachs and bladders. Sometimes the difference in weight and cost between the two forms of construction is marginal and it may not matter very much which is used. In other cases the difference is very great. As we have seen, a tent is always much lighter and cheaper than any equivalent building made from continuous panels or concrete or masonry. In coach building, the old-fashioned Wayman saloon car body, circa 1930, which consisted of a wooden space frame covered with padded fabric, was very much lighter than any of the pressed metal shell bodies which have been used since. In these days of expensive petrol, the Wayman body might well be revived. There is, however, an idea about that monocoque shells are somehow more modern and more advanced than space frames, which are sometimes considered to be primitive and rather Heath Robinson. Although a good many engineers who ought to know better subscribe to this view, there is in fact no objective structural justification for it. When it comes to carrying loads which are primarily compressive, the space frame is always lighter and usually cheaper than the monocoque. The weight penalty for using a monocoque, however, is less severe when the loads are high in relation to the dimensions, and this, in conjunction with other considerations, may justify the use of shells in some instances. However, for large, lightly loaded structures, such as rigid airships, the space frame or trellis structure is the only practicable one. The alternative for lighter-than-air transport is not a vast monocoque airship made from an engineer's dream of shiny aluminium plates, but a pressurized bag or blimp. The transition from the stick and string and fabric construction of the early aircraft to modern monocoques was not dictated by some sudden surge of fashion but was a strictly logical step in aircraft design once certain loads and speeds were reached. As we have said, regarded solely as a means of taking compression and bending, the monocoque is always heavier than the space frame, but the extra weight required gets less in proportion as the load on the structure increases. On the other hand, regarded as a means of resisting shear and torsion, the monocoque is more efficient than the space frame. As aircraft speeds increase, so do the requirements for torsional strength and stiffness. There comes therefore a transition point, which was reached in the 1930s, when it pays, in terms of structure weight, to change over the construction of airframes from spaceframe to monocoque. This is especially the case with monoplanes. Thus modern aircraft are usually built as continuous shells, using aluminium sheet, plywood or fiberglass for the skin. We see an equally logical reversion to spaceframe construction in modern hang gliders, which are very light indeed. The need to resist large torsional loads is almost confined to artificial structures such as ships and aircraft. As we said in Chapter 12, nature nearly always manages to avoid torsion, and thus, at least as far as large animals are concerned, monocoques or exoskeletons are uncommon. Most sizable animals are vertebrates and therefore highly sophisticated and successful spaceframes, not very different in their structural philosophy from biplanes and sailing ships. The avoidance of severe torsional requirements is very noticeable in birds and bats and pterodactyls. It is this which enabled these animals to retain their light spaceframe construction when they took to the air. Aircraft designers, please note. Blown-up structures. It is sometimes interesting to speculate about the technological ifs and buts of history. If Isambard Kingdom Brunei had come upon the railway scene a very few years earlier than he did, it is probable that most of the railways of the world would have standardized on a gauge of 7 feet instead of using his rival George Stephenson's coal wagon gauge of 4 feet 8 pound-inches, which derived from the Roman chariots. The Stephenson gauge has proved something of a handicap, as Brunei predicted it would. If they had a wider gauge today, the railways might perhaps be in a stronger position, technically and economically, than they are. If so, the world might be slightly different. On the other hand, if an effective pneumatic tire had been available around 1830, we might have gone direct to mechanical road transport without passing through the intervening stage of railways at all. In that case, the present-day world would have been even more different. In fact, the pneumatic tire was invented about 15 years too late. It was patented in 1845 by a young man called W. Thomson, then aged 23. Thomson's tire was surprisingly successful technically, but by that time the railways were well established, and the rail interests combined with the horse interests to promote absurd and restrictive legislation, which had the effect of delaying the development of the motor car until the turn of the century. Since the bicycle was never thought to constitute a serious threat either to trains or to horses, its development was legally permitted in Victorian times. The pneumatic tire was revived with considerable success, for use on cycles, by J. B. Dunlop in 1888. Dunlop made a fortune out of it, but by that time Thomson was dead and his patent had expired. With solid tires, lorries are limited to something like 15 miles per hour, and cars cannot go very much faster. Thomson's invention has not only made fast and cheap road transport practicable, it has also enabled aircraft to operate from dry land. Without pneumatic tires, we should probably have to use some form of seaplane. Tires, of course, have the function of spreading and cushioning the load beneath the wheels of a vehicle, and in this they are extremely successful. However, tires are really only one example of a whole class of blown-up structures. Quite apart from any cushioning effects, blown-up structures provide a very effective way of evading the serious penalties in weight and cost which are incurred when we try to carry light loads over a long distance in bending or in compression. What such a structure does is to carry the compression, not in a solid panel or column which is liable to buckle, but by compressing a fluid, such as air or water. Thus the solid parts have only to sustain tension forces, which, as we have seen, involve very much less weight and cost than compression. In technology, the idea of using blown-up structures in an intelligent way is not new. Around 1000 BC, the upriver boatmen of the Tigris and the Euphrates were making boats and rafts from blown-up animal skins. These boats voyaged downstream carrying, not only produce for sale in the cities of the plains, but also mules or donkeys. On arrival at their destination, the skins were deflated and returned to their home ports, overland, on the backs of the pack animals. Nowadays pneumatic boats are common, and so are pneumatic tents and furniture. They are often packed up and carried around. On cars. The air-supported roof was invented by the great engineer F. W. Lanchester in 1910. It consists simply of an inflatable membrane, attached at its edges to the ground. It is kept up by air at very low pressure provided by a simple fan arrangement. Although it has to be entered and left by means of an airlock, this is not usually a very serious handicap in view of the other advantages. Lanchester's roof allows large areas to be covered very easily and cheaply, but its use is at present confined to things like greenhouses and covered tennis courts. It is prevented from being used for factories or houses by rather grandmotherly building regulations. Of course, one does not have to use air. The sandbag is really another way of doing the same sort of thing, and so are draconi barges, which are simply large elongated floating sacks, filled with oil or water. They are used on the upper Amazon for transporting oil and are returned, deflated, but not on donkeys, in much the same way as the skin boats of the Euphrates. They are also used to bring fresh water to hotels in the Greek islands for the baths of the tourists. Blown-up structures probably deserve to be developed much further than they have been for technological uses. However, the great exploiters of this form of construction are plants and animals. Both plants and animals are in business as chemical factories and are, in consequence, full of complicated and messy fluids. Nothing could be more natural and economical, for instance, than to make a worm in the form of an elongated bag stuffed, so to speak, with the worm's squidgy insides. Clearly, this works very well, and in fact it seems so natural and so economical that one wonders why animals ever bothered to acquire skeletons made from brittle, heavy bones. Would it not be much more convenient, for instance, if men were made like octopuses or squids or elephants' trunks? One view of the question, which was put to me by Professor Simkis, is that animals never really meant to have skeletons at all. What may have happened was that the earliest bones were simply safe dumping grounds for unwanted metal atoms in the body. Once animals had produced solid mineral lumps inside their bodies, then they might as well make use of them as attachments for muscles. Wire wheels. It won't be a stylish marriage, I can't afford a carriage, but you'll look sweet upon the seat of a bicycle made for two. Harry Dacre, Daisy Bell. In the traditional wooden carriage wheel, the weight of the vehicle is taken in compression by each of the spokes in turn. A carriage is therefore rather like a centipede with a great many long legs which, taken together, are heavy and inefficient. This fact seems first to have dawned upon that remarkable and eccentric man, Sir George Cayley, 1773 to 1857. Cayley was one of the earliest and most brilliant of the aircraft pioneers, and he was interested in making better and lighter landing wheels for his aircraft. As early as 188 it occurred to him that a great deal of weight could be saved by designing wheels in which the spokes were in tension rather than in compression. This thinking led, eventually, to the development of the modern bicycle wheel, in which the wire spokes are in tension while the compressive forces are taken by the rim, which can be quite light and thin, since it is well stabilized against buckling. In conjunction with the pneumatic tire, the wire wheel made bicycling practicable for ordinary people, with considerable social consequences, from Daisy Bell onwards. The saving in weight is, however, mostly confined to large lightly loaded wheels, such as bicycle wheels. When the wheel becomes smaller and the loads larger, there is generally not much advantage to be gained from using tension spokes. In modern sports cars, pressed steel wheels are very little heavier than wire wheels, which are usually not worth the bother and expense. On choosing a better material, and what is a better material anyway? Nature may be supposed to know her business when she chooses between the various possibilities in the way of biological tissues, but mere men, even very great men, seem to have the strangest ideas about materials. According to Homer, the bow of Apollo was made of silver *, a metal whose strain energy storage is negligible. In a rather later age we were told that the floors of heaven were made of gold, or alternatively of glass, both very unsuitable substances. Poets are always quite hopeless about materials, but most of the rest of us are not much better. In fact, very few people ever think rationally about the subject at all. Quirks of fashion and prestige seem to play a large part in the matter. Gold is not really a very good material for watches, nor is steel for office furniture. The Victorians insisted on making all sorts of improbable articles, such as umbrella stands, out of cast iron, and there is the story of the African chief who had his palace made out of the same substance. Although the choice of materials is sometimes irrational and eccentric, more often it is highly traditional and conservative. Of course, there is sound reason behind a good deal of traditional material selection, but it is so mixed up with unreason that it is difficult to separate the two. Artists from Lewis Carroll to Dali have discovered that it is possible to impart a considerable psychological shock merely by implying that some familiar object might be made from an apparently unsuitable material, such as rubber or bread and butter. Engineers are very susceptible to these effects. They would be a good deal shocked nowadays at the idea of a large wooden ship. Our ancestors were much more shocked at the idea of an iron one. The acceptability of various materials changes with time in curious and interesting ways. Thatch is a case in point. Thatch was once the cheapest and least regarded of roofing materials, but in the poorer country districts it often had to suffice even for the roofs of churches. During the 18th century, when these parishes became richer, subscriptions were raised to replace the thatch by slates or tiles. Sometimes the money was inadequate to do the whole job, and in these cases the thatch had perforce to be left on those areas of the church roof which were not likely to be seen by passers-by. Only the side which faced the main road was tiled. Nowadays the balance of prestige is reversed, and in the home counties thatched roofs are the pride and joy of the wealthier of the business fraternity. Materials, fuel and energy. The 20th century may be known to posterity as the age of steel and concrete. It may also be known as the age of ugliness, and perhaps by other unpleasant names as well, such as the age of waste. It is not only engineers who are obsessed by steel and concrete, and quite indifferent to appearances. Politicians and the man in the street seem to have caught the same infection. The disease seems to have originated 200 years ago with the Industrial Revolution and cheap coal, which led to cheap iron, which led to iron steam engines fitted to turn that coal into cheap mechanical energy, and so on round and round in ever more energy-intensive circles. Thus coal and oil store a great deal of energy packed into a small volume. Engines process a great deal of this energy very quickly and within a small space. They then deliver the energy as electricity or mechanical work in concentrated forms. On this concentration of energy our whole contemporary technology rests. The materials of this technology, steel, aluminium and concrete, themselves require a great deal of energy to manufacture them. How much energy is indicated in Table 6. Because they need so much energy to make them, these materials can only be employed with profit within an energy-intensive economy. We are not only investing money capital in a technical device, we are also investing energy capital, and in both cases it is necessary to secure a fair return on the investment. Table 6 approximate energies required to produce various materials. Material N equals energy to manufacture joules times 10^9 per ton. Oil equivalent tons steel, mild, 61 times 5 titanium 820 aluminium 256 glass 24 0 times 6 brick 60 times 15 concrete 4 times 00 times 1 carbon fiber composite 4100. Wood, spruce, 1 times 00 times 0 25 polyethylene 45 1 times 1. Note: all these values are very rough and no doubt controversial, but I think that they are in the right region. The value given for carbon fiber composites is admittedly a guess, but it is a guess founded upon many years of experience in developing similar fibers. In spite of the high cost and increasing scarcity of energy, the trend in the energy-intensive direction is increasing rather than diminishing. Advanced engines, such as gas turbines, process more and more energy, more and more hectically, within less and less space. Advanced devices require advanced materials, and the newer materials, such as high-temperature alloys and carbon fiber. Plastics consume more and more energy in their manufacture. Most probably this kind of thing cannot go on for very much longer, for the whole system is entirely dependent upon cheap and concentrated sources of energy, such as oil. Living nature may be regarded as an enormous system for extracting energy, not from concentrated but from diffuse sources, and then using that energy with the uttermost economy. Many attempts are on foot at present to collect energy for technology from diffuse sources, such as the sun, the wind, or the sea. Many of these are likely to fail because the energy investment which will be needed, using conventional collecting structures built of steel or concrete, cannot yield an economic return. A quite different approach to the whole concept of efficiency will be needed. Nature seems to look at these problems in terms of her metabolic investment, and we may have to do something of the same kind. It is not only that metals and concrete require a great deal of energy, per ton, to manufacture. Table 6, but also that, for the diffuse or lightly loaded structures which are usually needed for systems of low energy intensity, the actual weight of devices made from steel and concrete is likely to be very many times higher than it would be if we used more sensible and more civilized materials. As we shall shortly see, timber can be one of the most efficient of all materials in a strictly structural sense. For large dimensions and light loads, a wooden structure is many times lighter than one made from steel or concrete. One of the difficulties with timber, in the past, has always been that trees take a long time to grow and wood is slow and expensive to season. Probably the most important development in materials during the last few years has been that made by the plant geneticists who have been breeding fast-growing varieties of commercial timbers. Thus varieties of Pinus radiata, Weymouth pine, are now being planted which, in favorable conditions, will increase in diameter by up to 12 centimeters per year and may be fit for felling, as mature timber, in 6 years. So there is a good prospect of timber becoming a crop which can be grown on a short time cycle. Nearly all the energy which is needed to make it grow is provided, free, by the sun. Presumably, when one has finished with a timber structure, it could be burnt to yield up most of the energy which it has collected while it was growing. This is, of course, in no way true of steel or concrete. Again, timber used to need lengthy and expensive seasoning in heated kilns, which used up a good deal of energy. As a result of recent research, it is now possible to season sizable softwood scantlings in 24 hours, at a very low cost. These are very important developments in relation to structures and to the world energy situation, and it behoves us to take account of them. Some algebraical analysis of the structural efficiencies in various roles arid in terms of weight, of different materials, is given in Appendix 4. The design of a number of high-technology structures, such as aircraft, is largely controlled by the criterion E-rho, that is to say, by the specific Young's modulus which governs the weight cost of the overall deflections. It happens that, for the majority of traditional structural materials, molybdenum, steel, titanium, aluminium, magnesium and wood, the value of E-rho is sensibly constant. It is for this reason that, over the last 15 or 20 years, governments have spent such large sums of money in developing new materials based on exotic fibers such as boron, carbon and silicon carbide. Fibers of this sort may or may not be effective in aerospace, but what seems to be certain is that not only are they expensive but they also need large amounts of energy to make them. For this reason their future use is likely to be rather limited, arched, in my own view, they are not likely to become the people's materials of the foreseeable future. Table 7. The efficiency of various materials in different roles. Young's modulus, specific gravity. Material EMN M2 rho grams C.C. E rho. Steel 210,007 times 8 25,197 times 5 titanium 120,004 times 5 25,240 11 times 0 aluminium 73,002 times 4 25,310 15 times 0 magnesium 42,001 times 7 24,380 20 times 5 glass 73,002 times 4 25,360 17 times 5 brick 21,003 times 0 7,159 times 0 concrete 15,002 times 5 6,160 10 times 0 carbon fiber composite 200,002 times 0 100,729 times 0 wood, spruce, 14,000 0 times 5 25,750 48 times 0. The requirement for a strict and expensive control of overall deflections is likely to be a very limited one. However, as we have seen, the weight cost, and often the money cost, of carrying compressive loads is frequently very high. The weight cost of carrying a compressive load in a column is governed, not by E rho, but by. The weight cost of a panel is controlled by. Appendix 4. These requirements are summarized in Table 7. It will be seen that there is a large premium on load density, thus steel comes out rather badly, even compared with bricks and concrete. Furthermore, for many lightweight applications, such as airships or artificial limbs, wood is even better than carbon fiber materials, besides being much cheaper. In Table 8 these virtues are expressed in terms of energy cost. Table 8 the structural efficiency of various materials in terms of the energy needed to make them. Material energy needed to ensure a given stiffness in the structure as a whole. Energy needed to produce a panel of given compressive strength steel 1 titanium 39 aluminium 4 2 brick 0 times 4 0 times 1 concrete 0 times 3 0 times 0 5 wood 0 times 0 2 0 times 0 0 2 carbon fiber composite 17 17 times 0. Here the advantage of the traditional materials, wood, brick and concrete, is overwhelming. This table makes one wonder whether the pursuit of materials based on exotic fibers is really justified. What really pays off for most of the common purposes of life is not carbon fibers, but holes. Nature tumbled to this a long time ago when she invented wood, and so did the Romans when they started to build churches from empty wine bottles. Holes are enormously cheaper, both in money and in energy, than any conceivable form of high-stiffness material. It would probably be better to spend more time and money on developing cellular or porous materials and less on boron or carbon fibers. Chapter 15 A chapter of accidents. A study in sin, error, and metal fatigue. Have you heard of the wonderful one-horse sleigh that was built in such a logical way? It ran 100 years to a day, and then, of a sudden, it. Oliver Wendell Holmes, The One-Horse Sleigh. The entire physical world is most properly regarded as a great energy system, an enormous marketplace in which one form of energy is forever being traded for another form according to set rules and values. That which is energetically advantageous is that which will sooner or later happen. In one sense, a structure is a device which exists in order to delay some event which is energetically favored. It is energetically advantageous, for instance, for a weight to fall to the ground, for strain energy to be released and so on. Sooner or later the weight will fall to the ground and the strain energy will be released, but it is the business of a structure to delay such events for a season, for a lifetime or for thousands of years. All structures will be broken or destroyed in the end just as all people will die in the end. It is the purpose of medicine and engineering to postpone these occurrences for a decent interval. The question is, what is to be regarded as a decent interval? Every structure must be built so as to be safe for what may reasonably be considered an appropriate working life. For a rocket case this might be a few minutes, for a car or an aircraft, 10 or 20 years, for a cathedral perhaps 1,000 years. Oliver Wendell Holmes's one-horse shay was constructed to last for 100 years, neither more nor less, and it disintegrated, exactly as planned, on the 1st of November 1855, just as T.J. Parson had reached fifthly in the composition of his sermon. But, of course, this was nonsense. Again, the egregious but heroic Mr. Honey in Neville Shoots No Highway predicts the failure of the tail of the Reindeer airliner from metal fatigue after exactly 1,440 flying hours, plus or minus a day or so. This again was nonsense, as Neville Shiite must have known, being an experienced aircraft designer. It is impossible, in practice, to plan for a safe life of exactly so many hours or years. We can only consider the problem in statistical terms and in the light of accumulated data and experience. We then build in whatever margin of safety seems reasonable. All the time we are working on a basis of probabilities and estimates. If we make the structure too weak we may save weight and money, but then the chance of the thing breaking too soon will become unacceptably high. Contrariwise, if we make a structure so strong that, in human terms, it is likely to last forever, which is what the public would like, then it will probably be too heavy and expensive. As we shall see, there are many cases where more danger is incurred by extra weight than is avoided by the corresponding increase of strength. Because we are necessarily working on a statistical basis, when we design a practical structure for a realistic life we have to accept that there is always some finite risk, however small, of premature failure. As Sir Alfred Pugsley points out in his book The Safety of Structures, it is just at this rather interesting stage that we may have to abandon a strictly logical approach to the problem. As Pugsley says, the human emotions are quite exceptionally sensitive to the fear of structural failure, and the layman clings with great tenacity to the idea that any structure or device with which he is personally associated should be unbreakable. This crops up in all sorts of connections, sometimes it does no harm, sometimes the effect is counterproductive. During the last war aircraft designers had the choice, to some extent, of trading off structural safety against other qualities in the aircraft. Now the losses of bomber aircraft by enemy action were very high, something like 1 out of 20 in each sortie. Against this, the losses from structural failures were very few, much less than one aircraft in 10,000. The structure of an aeroplane accounts for practically a third of its total weight, and it would have been rational to have slimmed the structural parts of the bombers in return for other advantages. If this had been done there would have been some small increase in the structural accident rate, but the weight that would have been saved could have been invested in more defensive guns or in thicker protective armor. In that case there would no doubt have been a significant reduction in the net, or overall, casualty rate. But the airmen would not hear of anything of the kind. They preferred the big risk of being shot down by the enemy to the smaller risk of the aircraft breaking up in the air for structural reasons. Pugsley suggests that the feeling that it is in some way outrageous for a structure to break may be inherited from our arboreal ancestors, who were frightened, above all things, that the trees in which they lived might break beneath them, when down would come baby and cradle and all. And besides, the ancestors and their babies would fall into the mouths of their enemies on the ground, such as saber-toothed tigers or whatnot. Whether this is the real reason or no, engineers have to take these sort of feelings into account, even though the extra weight incurred may involve dangers of its own. The accuracy of strength calculations. It is implicit in any rational approach to questions of strength and safety that the engineer should be able to predict, with sufficient accuracy, the strength of a proposed structure when it is new, even if he is in doubt about how long it may be expected to last. While this may be roughly the case for simple structures such as ropes and chains and straightforward beams and columns, as we saw in Chapter 4, it is just not true at all for the more elaborate and critical artifacts, things like aircraft and ships. Since there is available a great body of accumulated experience with various kinds of structures, since there also exists a vast and highly mathematical literature on the subject, and since academic elasticians, in their pride, deliver endless lectures about the theory of structures, that statement might be regarded as sticking one's neck out. However, it is true. Consider, for instance, the statistics for the strength of aircraft. Since the saving of weight is important and since the consequences of failure are very horrible, a great deal of care and thought is naturally given to the structural design of aeroplanes, and every detail is meticulously checked. The drawings and calculations are made by highly skilled designers and stressmen and draftsmen, using the most scientific methods. When these people have done their sums, the strength calculations are checked, quite independently, by an entirely different set of experts. Thus the strength predictions which are finally arrived at are about as accurate and painstaking as is humanly possible. Finally, and to make quite certain, an actual full-scale airframe is tested to destruction. It is not possible to give really up-to-date results because so few different types of aeroplane have been ordered in recent years that the figures are not statistically significant. However, when aircraft were simpler and cheaper, a comparatively large number of designs reached at least the prototype stage. Between 1935 and 1955, something in the region of 100 different kinds of aeroplane were built and tested to destruction in this country. Thus the results for this period form a fairly reliable guide with some sort of statistical basis. Naturally, the actual figures of the required strengths for these different aircraft varied a great deal, according to the size and type of aeroplane. However, each design team could be said to be aiming at that strength which is known in the jargon of the aircraft trade as 120% fully factored load. If structural design were anything like an exact profession, one would expect the various test results, when plotted on a curve or histogram, to cluster pretty closely around the value for 120% fully factored load, give or take a very little. In other words, the results should produce a narrow normal or bell-shaped distribution curve, much like Figure 1. As is fairly well known, nothing of the sort happened. When the results are plotted, the histogram looks more like Figure 2. The experimental strengths tend to be randomly distributed between about 50% and 150% of the required or fully factored load. That is to say, even the most eminent designers cannot be relied upon to predict the strength of an aeroplane within a range of 3 to 1. Some of these aircraft were less than half as strong as they should have been, others were much too strong and therefore considerably heavier than they needed to be. Figure 1. Expected statistical distribution of experimental aircraft strengths, schematic diagram. Figure 2. Actual distribution of strengths of airframes broken in test frame, 193S5S, very approximate schematic diagram. When it comes to ships, there are really no data on which one can base this sort of judgment, for the reason that ships are almost never tested to destruction under laboratory conditions. It is therefore impossible to tell how good or bad naval architects are at their job, at least as far as strength predictions are concerned. However, as we said in Chapter 5, the number of structural accidents to ships is considerable, and it seems very possible that the number of accidents per ton-mile is increasing at the present time. With regard to bridges, the problem of strength calculation is in some respects easier than with ships and aircraft, since the loading conditions are less varied. Nevertheless, the number of failures in modern bridges is quite significant. Designing by experiment. Now, in building of chassis, I tell you what, there is always somewhere a weakest spot in hub, tire, felloe, or spring or thill, in panel, or crossbar, or floor, or sill, in screw, bolt, thoroughbrace, lacking still, find it somewhere you must and will. Oliver Wendell Holmes, The One-Horse Shay. The fallibility of the theoretical design processes, of course, the reason for the insistence on the experimental strength testing of all aircraft. However, the benefits of an experimental approach extend still further. We have assumed that it ought to be the designer's aim for a structure to fail the first time it is tested, exactly at the required load. But even the most scientifically designed structure is very unlikely to be of consistent strength throughout all its parts, like the legendary Shear, and so on for many components and many lines of verse. The wheels were just as strong as the thills, and the floor was just as strong as the sills, and the panels were just as strong as the floor. On the test frame the structure breaks at the weakest place, all the rest of the structure is therefore of greater strength. If an airframe fails initially at just the required 120%, it follows that much the greater part of the structure is too strong for its purpose, and this extra strength is completely wasted. But we have no means of knowing where and how to lighten the structure. Repeated tests on large structures are expensive and time-consuming, but, where time and money allow, it is better to arrange, if possible, for the initial failure to occur at a load comfortably below the official 120%. The weak place thus indicated can then be strengthened and the whole structure retested, and so on. The wartime Mosquito bomber, which was one of the most successful aircraft in history, failed initially at 88% of the factored load, in the rear wing spar. The aeroplane was then progressively strengthened up to a figure of 118%. It was owing, partly, to the exceptionally light and strong airframe that the performance of this aircraft was outstanding. This is, roughly speaking, the Darwinian method, which nature seems to rely on to develop her own structures, though she seems to be in less of a hurry and less mindful of the value of life than are most civilized human engineers. It is also, to a notable extent, the method employed by the makers of cars and other cheap, mass-produced goods. These people tend to make their products deliberately too weak for their purpose and to rely upon customers' complaints to detect the significant faults. Thus a great deal of the strength-predicting element of design boils down to a sort of game in which we try to spot the weakest link in a load-bearing system. The more complicated the structure, the more difficult and unreliable this becomes. Fortunately, the design of a great many structures, from furniture and buildings to aeroplanes, is rescued from becoming a completely ridiculous process by the fact that the stiffness requirements may be more exacting than the strength requirements. Thus, if the structure is made stiff enough for its purpose, it may then very well be sufficiently strong. Since the deflections in a structure depend upon its general character rather than upon the existence of a weakest link, stiffness predictions are much easier to make, and more reliable, than strength predictions. This is what we really mean when we talk about designing a thing by eye. How long will it last? This also said Fossilides, a tiny rock-built citadel is finer far, if ordered well, than all your frantic Ninevehs. Fossilides, translated by Sir Maurice Bowrer. In discussing the strength and stability of the masonry cathedrals, Professor Jack Heyman has laid down the principle that if a structure will stand for 5 minutes, it will stand for 500 years. For masonry structures built upon rock this is, broadly speaking, true. However, many cathedrals and other buildings have been founded upon soft ground. If this soft soil creeps, Chapter 7, which happens quite often, curious things will happen, such as the Leaning Tower of Pisa. Such movements take time and can often be predicted, but they are very expensive to put right, and a certain number of buildings, both ancient and modern, fall down or have to be demolished for this reason. In most types of structure, rot and rust are very active agents of decay. It is partly the fear of rot which has turned engineers and architects in Britain against timber. However, the poor benighted foreigners in America and Canada and Scandinavia and Switzerland, who build between them about 1,500,000 wooden houses each year, do not seem to be troubled with rot to the same extent, and it might be a good idea to see how they manage these things. The use of wood is greatly on the increase in these countries. Timbers vary a great deal in their natural resistance to decay, and Lloyd's Register allocates a fixed number of years of life to each of the different timbers which are used in shipbuilding. However, with modern knowledge and methods of treatment, it should be possible to get a practically indefinite life from almost any kind of wood. Most metals corrode in service. Modern mild steel rusts very much worse than Victorian wrought iron or cast iron, and so rust is, to some extent, a modern problem. Because the cost of labor is high, the cost of the painting and maintenance of steelwork is high. This is one good reason for using reinforced concrete, since steel embedded in concrete does not rust. In fact, large modern ships, such as tankers, are constructed for a life of about 15 years. On the whole, it is cheaper to scrap than to paint. The life of cars is even shorter, usually for the same reason. It is true that for some structures one could use stainless steel, but it is by no means always proof against corrosion, and stainless steels are expensive and awkward to fabricate. Besides this, the fatigue properties of stainless steels are usually bad. These are some of the reasons for choosing aluminium alloys, but, apart from the extra cost, there are a number of cases where the stiffness of aluminium has proved inadequate. The difficulty of welding aluminium is also a handicap. Some communist countries see a great future for aluminium and have invested largely in aluminium plants. The London stock markets were considerably shaken by the Tube Investments British aluminium takeover bid in 1961. However, the market for aluminium has not expanded to anything like the extent which was anticipated by the businessmen concerned in this transaction. In any case, it requires more energy to make aluminium than to make steel. Even if the material of a structure does not deteriorate, its life may be subject to statistical effects which are sometimes calculable, and sometimes not. Many structures are likely to be broken only in rather exceptional circumstances, and it may be a long time before these circumstances arise. Freakishly high waves, in the case of a ship, and exceptionally severe upward gusts with aircraft are cases in point. Some structures are likely to be broken only by unusual combinations of events. For a bridge, this might be the coincidence of very high winds with exceptional traffic loads. Although such eventualities ought to be provided for, it may be many years before they actually happen. So an essentially unsafe structure may stand for a long time, simply because it has never been fully tried. Responsible engineers do, of course, try to predict things of this sort and to make structural provision for them, but in many cases such peak loads shade off into what the insurance companies call acts of God. If a ship runs into a large bridge, destroying both the bridge and the ship, as happened recently in Tasmania, it is very difficult to see what either the naval architect or the bridge designer could have been expected to do about it from the structural point of view. The problem is one not for the structural engineer but for the local pilotage association. Again, aircraft cannot be designed to be flown into mountains. We do, to a certain extent, design cars to be driven into brick walls without killing the passengers, but then we do not expect the car to be of much use afterwards. Metal fatigue, Mr. Honey and all that. One of the most insidious causes of loss of strength in a structure is fatigue, that is to say, the cumulative effect of fluctuating loads. The dramatic possibilities of fatigue in metals were first exploited in popular literature in 1895 in Kipling's account of what happened when the propeller of the Grotkow dropped off somewhere in the Bay of Biscay because of a fatigue crack in the tail shaft. Kipling went out of fashion, but public interest in fatigue was revived in 1948 by Nevil Shute's No Highway. The success of this story, both as a book and as a film, was no doubt partly due to the character of Mr. Honey, the archetypal boffin, but perhaps still more to the 3 comet disasters, which occurred not very long afterwards. As Whistler remarked some time ago, nature keeps creeping up on art. The circumstances of the comet accidents were not very different from those imagined in No Highway, except that many more lives were lost and a great deal of damage was done to the British aircraft industry. As a matter of fact, engineers' knowledge of fatigue effects in metals goes back rather over 100 years. Indeed, it was not long after the Industrial Revolution that it began to be noticed that the moving parts of machinery would sometimes break at loads and stresses which would have been perfectly safe in a stationary component. This was especially dangerous in railway trains, whose axles would sometimes break off suddenly and for no apparent reason after they had been in service for a time. The effect soon came to be known as fatigue, and the classical researches on the subject were carried out during the middle years of the 19th century by a German railway official called Wöhler, 1819 to 1914. From his photograph here, Wöhler looks exactly what one would expect a German 19th century railway official to look like, but he did a very useful job. As we said in Chapter 5, even though there may be a high local stress at the tip of a notch or a crack, the crack will not extend, so long as it is shorter than the critical Griffith length, because making it spread requires work to be done against the work of fracture of the material. However, when the stress in the material is a fluctuating one, slow changes take place within the crystalline structure of the metal, and this is particularly likely to happen in the region of a stress concentration. These changes have the effect of reducing the work of fracture of the metal in such a manner that the crack is able to extend, very slowly, even though it may be much shorter than the critical length. In this way, a tiny unseen crack may start from any hole or notch or irregularity in a stressed metal and may spread across the material, which is not, as a whole, changed in any obvious way. Sooner or later, such a fatigue crack will reach the critical length for an ordinary common or garden crack. When this happens, the crack will immediately speed up and run right across the material, often with very serious consequences. It is usually quite easy to diagnose a fatigue crack after failure because of its characteristic striped or banded appearance. Before rupture, however, an incipient fatigue failure may be practically impossible to spot. Naturally, metallurgists and others do a great deal of experimental fatigue testing on their materials, and a great many different types of testing machine are now available for the purpose. It is common to consider the fatigue properties of a metal in terms of a reverse stress, plus or minus S, that is to say, the sort of stress which would occur in a rotating cantilever, such as the axle of a vehicle. There are ways of converting these results to other conditions of fluctuating stress. This reverse stress, plus or minus S, is usually plotted on a graph against the logarithm of the number, n, of times the stress has to be applied to a specimen to cause failure. This is sometimes called an SN diagram. The SN diagram for a typical steel would look like Figure 3. It will be seen that the curve is a dog-legged affair which flattens off after about 1 million reversals, which might be equivalent to about 3,000 miles of service for the axle of a car or train, or about 10 hours of running for an ordinary car engine, which, of course, goes round much faster than the wheels. The existence of a definite fatigue limit of this nature for materials like iron and steel constitutes a great comfort to the engineer. If his engine or his vehicle will run for 10.6 or 10.7 revolutions, which may only take a few hours, then there is some hope of its being safe indefinitely. But fatigue is a danger which always needs to be considered. Figure 3. Typical fatigue curve for iron or steel. Aluminium alloys do not have a definite fatigue limit but tend to tail off, something after the fashion of Figure 4. This makes them more dangerous to use and accounts for some apparently old-fashioned prejudices in favor of steel for use in machinery and other structures. The comet accidents, which occurred in 1953 and 1954, naturally caused consternation and well-justified alarm. The investigation of these accidents by Sir Arnold Hall and a large team of experts was a classical feat, not only of engineering detection, but also of deep-sea salvage. The broken parts of one of the aircraft, which had fallen into the Mediterranean, had to be dredged up from a depth of over 300 feet or 50 fathoms. The salvage people managed to recover practically the whole of the aeroplane, and the innumerable fragments covered the floor of a large hangar at Farnborough. As far as I remember, no piece was more than 2 or 3 feet across. Figure 4. Non-ferrous alloys such as brass and aluminium frequently do not show any definite fatigue limit. The Comet was one of the earliest airliners to have a pressurized fuselage. The main purpose of this was, of course, to spare the passengers from the discomfort and danger of the atmospheric pressure changes associated with change of altitude. In the old days, when flying over the Rocky Mountains, one used to have to eat one's lunch while wearing an oxygen mask. This now ranks as one of those lost skills. In a pressurized aircraft, the fuselage becomes, in effect, a cylindrical pressure vessel, not unlike a very thin-walled boiler, which is pressurized and relaxed every time the aircraft climbs and descends. The lethal mistake in the design of the Comet lay in not realizing sufficiently the danger of fatigue occurring at stress concentrations in the metal of the fuselage under these circumstances. The Comet was built from aluminium alloys, and most of de Havilland's previous experience had been gained with wooden aeroplanes, such as the triumphantly successful Mosquito. I am not suggesting for a moment that de Havilland's very able design staff did not know a lot about fatigue, but it is possible that the danger of fatigue in aluminium alloys may not have burnt itself sufficiently deeply into their collective consciousness. Wood is much less susceptible to this danger than metals, which is one of its great advantages. In each of these accidents, cracks seem to have started from the same small hole in the fuselage and spread, slowly and undetected, until they reached the critical Griffith length. Whereupon the skin tore catastrophically and the fuselage exploded like a blown-up balloon. By repeatedly pressurizing a Comet fuselage in a large tank of water at Farnborough, Sir Arnold Hall was able to reproduce the effect so that it could be observed, as it were, in slow motion. Part of the trouble about the Comet accidents was that the fatigue cracks, which must have existed, were never spotted by an inspector, perhaps because he was not expecting to find them, but more probably because they were too short to be seen easily. Nowadays aircraft fuselages are designed to contain with safety cracks up to about 2 feet long, and one would think that so long a crack could hardly fail to be seen in good time. There is, however, the story about the 2 cleaners at London Airport. These ladies finished sweeping out the cabins of an empty airliner late one night. They shut the door and went down the steps onto the tarmac. "You've forgotten to switch off the light in the toilet, Mary." "How do you know?" "Can't you see it shining through the crack in the fuselage?" Accidents to wooden ships. Before the days of railways, nearly all the heavy traffic went by water. Besides the deep-sea trade and the continental trade and the inland trade by river and canal, there was an even larger coastal trade. Many thousands of little wooden brigs and schooners, of the kind caricatured by W. W. Jacobs, transported anything and everything, not only into the coastwise creeks and harbors, but to almost every possible or impossible beach. A ship would be grounded on the beach at high water and, when the tide fell, would unload her coal or bricks or lime or household furniture into carts which were driven alongside. When the tide rose again, she would slip away to sea and then go and do it all over again somewhere else. Naturally, this was rather a risky business, but during the 18th century most of the smaller vessels could afford to lay up and refit during the worst of the winter, when the crews could see something of their families and of the local pubs. This slightly idyllic and not exceptionally dangerous state of affairs was upset by the more competitive conditions of the 19th century. Under commercial pressures, vessels had to trade throughout the winter and could not afford, as a rule, to wait for weather. Indeed, the regularity of some of these little sailing ships would put a lot of modern goods trains to shame. But, of course, a price had to be paid. During the middle 1830s, an average of 567 shipwrecks occurred round the coasts of this country each year. As a result, a yearly average of 894 lives were lost. Whether these figures are better or worse, per ton-mile of goods delivered, than modern lorries, I do not know. At any rate, the public conscience was disturbed at the time and Parliament appointed a select committee to investigate the causes of shipwrecks. After hearing a great deal of evidence, the committee reported that, apart from minor causes, shipwrecks in this country could principally be attributed to the following conditions in ships. 1. Defective construction. 2. Inadequacy of equipment. 3. Imperfect state of repair. They pronounced that the defective construction of ships appears to have been greatly encouraged by the system of classification, i.e. the rules governing construction and repair of insured ships, which, from the year 1798 up to 1834, was followed by Lloyd's. The committee went on to add that the system by which the government measured ships for tonnage dues encouraged thoroughly unseaworthy shapes of hull. The bureaucratic mind does not seem to change very greatly through the centuries. To be fair, the problem of framing regulations for the strength and safety of ships, or any other kind of structure, is an extraordinarily difficult one. No doubt a certain amount of progress has been made in the matter since the 1830s. At the same time, and in a different sense, a great deal of technical progress has been prevented, especially by the various building regulations. As Pugsley points out in The Safety of Structures, it is inherently impossible to make regulations about the strength of structures which are proof against both falls and naves without preventing, or at best handicapping, development and innovation. Regulations for structural safety are presumably necessary, but some of them are not only stultifying, they can be the actual cause of accidents. To return to wooden ships, not only the clippers but the little brigs and brigantines and topsail schooners and barges, which were so beautiful and so satisfying, have all gone, and the yards that used to build them are now turning out yachts. The structural problem of a wooden yacht is both more and also less severe than that of larger vessels. Yachts' hulls are not bumped on shingle beaches while carrying cargoes of stone or coal, but they have a more difficult problem with regard to local impacts which their thin skins are not well fitted to resist. Now that long voyages in small yachts have become so fashionable, this question of the impact strength of the hull has become important. Yachts voyaging in deep waters have repeatedly been attacked and sunk by killer whales. These animals weigh about 6 tons and swim at around 30 knots. They seem to have a special hatred for small yachts, which they ram and hole below the waterline. This has now happened so often that the possibility cannot any longer be classed as an act of God, Poseidon presumably, but is a serious hazard which must be guarded against. It is probably impracticable to make the sides of a small yacht thick enough and strong enough to resist such an attack. The best thing to do would seem to be to provide some sort of inflatable flotation gear to keep the yacht afloat, and preferably sailable, after she has been holed. So far, those who have survived these attacks have done so by taking to the dinghy, which, naturally, gave most of them a very unpleasant time before they were picked up by a steamer after many days or weeks. More about boilers and pressure vessels, and something with boiling oil in it. For a considerable number of years before the railway system was completed, much of the passenger and express freight traffic was carried by steamship. During the first half of the 19th century, not only were there far more steamers running to more continental ports than is the case today, but there were also very numerous services between towns in Great Britain. Considerably the cheapest, and often the quickest and most comfortable route from London to such places as Newcastle, Edinburgh, or Aberdeen was by steamboat. Accidents were fewer in steamships than in sailing vessels only because there were many fewer steamships. Nevertheless, between 1817 and 1839, there were 92 major accidents to steamships in British waters. Of these, 23 were due to boiler explosions. This is nothing like as bad a record as that of the American river steamers a few years later, but it is quite bad enough. Some of the early boilers were made from unsuitable materials, such as cast iron. At least one cast iron boiler, that of the SS Norwich, duly burst and killed several people. Even when boilers were more or less properly constructed from wrought iron, they were very commonly neglected and allowed to rust through until they burst. This was the cause of the loss of the Shear on the Fame Islands in 1838. 5 people were rescued by Grace Darling's superb feat of seamanship. Again, a parliamentary committee was appointed, which reported in 1839 and produced an extensive, thorough, factual and almost incredible document. During the boom years of the expansion of the steam engine, sober, let alone competent, responsible or intelligent engine room staff were almost unobtainable, even at very high wages. These people treated their engines and boilers with a degree of ignorance and carelessness which almost passes belief. For instance, a steamer, on her passage from Ireland to Scotland, was perceived by her commander during the night, and in a smooth sea, to be going with much greater than ordinary velocity through the water. The engineer was not at his post. The captain inquired of the fireman how it was that the engines were going so fast. The man said he could not tell, for he had very little steam and had been firing hard nevertheless. The captain began to look about him and, approaching the chimney where the exposed safety valves were fixed, he perceived a passenger fast asleep with the greater part of the weight of his body resting on the flat, cheese-shaped, weights of the safety valve. This man had contrived, with some luggage, to make his bed there for warmth. On arousing and turning him off, the valve rose, the steam escaped with a roar which denoted its having attained a very elevated pressure. There was no mercurial gauge to indicate the pressure of the steam to the fireman, who was accustomed to keep it as near as he could to the blowing-off point, and not having heard it escape, he fired up believing his steam to be low, and he was too ignorant to ascertain the fact, though the increased speed of the engines should have informed him that something unusual had occurred. It is mentioned by several of our correspondents that engine men, firemen and even masters have frequently been caught sitting, or even standing, on the safety valves, or hanging weights and resting their bodies on the levers in order to raise the pressure of the steam at the moment of starting. The report goes on to say that it was also the practice to stow surplus bunker coal on top of the safety valve. The steamship Hercules blew up from this cause. Altogether, it is rather remarkable that only 77 lives were lost from boiler explosions in British steamers during the period under review. The record of the railways was about as bad as that of the steamships, and for much the same causes. There was a succession of very serious accidents extending over a period of 70 or 80 years. About the last of these occurred in 1909. A locomotive boiler blew up although the pressure gauge appeared to be showing zero pressure. It turned out that a workman had assembled the safety valve the wrong way round, so that it was incapable of blowing off at all. The gauge appeared to show no pressure for the simple reason that the needle had gone right round its full travel and was pressing against the wrong side of the stop pin. 3 people were killed and 3 more badly injured. In these latter days the number of boiler explosions has greatly diminished. This is partly because the manufacture and maintenance of steam boilers is now closely controlled by law and by the insurance companies, but perhaps more because the number of steam engines in service is now quite small, and those that do exist are nearly all large plants, such as power stations, which are presumably run by competent people. But, when is a boiler not a boiler? This is quite an interesting legal question. There exist in industry a large number of pressure vessels of one kind or another which are used in various manufacturing processes. Many of these vessels are of more complicated and less conventional design than traditional boilers, and they may be less obviously dangerous. In general, the control over their manufacture and use is less strict than for ordinary boilers. However, many of these vessels are heated by process steam or by hot oil under pressure, so that the consequences of fracture may be nearly as bad. It is well to bear in mind that the fatigue limit for the weld metal in mild steel structures exposed to wet steam may be as low as plus or minus 2000 p.s.L. In one instance in which I was concerned, 2 large rotating drums, used for making plastic-coated paper, had been converted from low-pressure oil heating to steam heating, using process steam at a higher pressure. To make certain, the insurance company's inspector had insisted that the Drums be strengthened internally by connecting the flat end plates to the cylindrical surface by means of a number of large triangular gussets, or brackets, cut from mild steel plate and welded in place. Both drums burst in service after being used for a short time with steam heating. From the drawings I calculated that, in the two drums, there were 48 individual places at which failure should have taken place. In fact, this was a pessimistic estimate. Failure actually occurred at only 47 places. By the grace of God, nobody was killed or seriously injured, but it was naughty of the insurance company's inspector, who, I expect, was a diligent and well-meaning little man. Another case was more tragic. A firm of chemical engineering contractors had bought in from elsewhere a mixing vessel which they installed as part of a plant they were constructing for a customer. Since this mixing vessel was intended to be heated by oil under pressure, the pressurized heating jacket had been subjected to a proof test with cold water. It had withstood a pressure of 65 psi without obvious damage before it was installed. However, when the plant was commissioned and the jacket was filled with very hot oil at only about 23 psi, the jacket burst after a few hours of service, spraying a man with oil at 280 degrees Celsius, from the effects of which he died a few days afterwards. According to the report of the official inspector, the accident could only have happened as a consequence of gross mismanagement by my clients, the firm of chemical engineers. As a result, these people had become involved in very elaborate and expensive litigation in the High Court. In fact, the official report of the accident was based on faulty observation of the broken remains and was quite misleading. The vessel had burst, not because it was mishandled by my clients, but because it was of incompetent design and manufacture. Although the technical cause of the accident was, in reality, of a slightly subtle nature, both my clients and also the people who actually made the vessel had assumed the design of such a thing to be a trivial problem. In fact, the vessel was never really designed at all in any sophisticated sense but was simply put together by eye in a backstreet welding shop. What actually happened was that, during the proof loading, the vital welds which held the pressurized heating jacket together were considerably distorted, although nobody noticed it at the time. In reality, these welds were so near to failure that a few reversals of stress, resulting from a much lower pressure in the jacket, sufficed to cause a fatigue failure, with disastrous consequences. This possibility should have been spotted by a competent trained engineer. In law, and perhaps in equity, the major blame lay with the people who had made the vessel, but I cannot help thinking that the danger should have been foreseen by a competent firm of chemical engineers. When I went to see these people, the managing director took me out to lunch. By way of making conversation, I said, "How many graduate engineers do you have in your organization, Mr. V? None, thank God. On cutting holes in things. Although it is generally rash to cut holes in an existing structure, some people seem unable to resist the temptation to do so. A case in point occurred with the Master aircraft. This aeroplane was built as an advanced trainer for the RAF just before the war. It had some of the performance, and many of the handling qualities, of the Hurricane and the Spitfire. In the emergency of 1940, some of the Masters were converted into operational fighters by installing 6 machine guns in the wings. The original trainer version of the machine had wire-operated control surfaces which, though they were perfectly satisfactory, gave a slightly softer response than those of a real fighter. Somebody therefore decided to change over from wire to rod control linkages in the fighter version of the Master. To make room for the rods which operated the rudder and elevator, suitable slots were cut in the rear bulkhead of the fuselage. Before long we were faced with a series of 3 fatal accidents. In each case the tail had come off. In flight. When we got the fuselage on the test frame, we found that its strength had been reduced to only 45% of the fully factored load. The moral is, I suppose, to leave well alone. A much better known accident of this type, in which a great many lives were lost, occurred with the troopship Birkenhead. This iron steamship had started life as a warship in 1846 with adequate strength and well supplied with continuous watertight bulkheads. When she was converted into a troopship, however, the War Office insisted that very large openings should be cut in the transverse watertight bulkheads so as to give more light and air and more apparent space for the troops. In 1852 the Birkenhead was dispatched to India, by way of the Cape, with 648 persons on board, including 20 women and children. By an error of pilotage, the ship struck an isolated rock about 4 miles off the South African coast. The vessel was badly holed forward, and, since the bulkheads had been cut away, all the troop decks in the forward part of the ship were flooded so quickly that many of the troops were drowned as they lay in their hammocks, the time being 2 a.m. Under the weight of the incoming water the flooded forepart of the ship broke off and sank almost immediately, leaving the survivors crowded into the afterpart, which sank more slowly. It was dark, the sea was full of sharks and the lifeboats were inadequate. The troops behaved with great courage and discipline, smartly fallen in on the afterdeck, while the women and children were sent ashore in such boats as there were. All of the women and children were saved but only 173 men survived, the rest were drowned or eaten by sharks. The most obvious effect of cutting holes in the bulkheads was, of course, that the various compartments in the ship flooded very rapidly, and this was undoubtedly the prime cause of the ship's loss. Fewer lives might have been lost, however, if the ship had not broken in two, and this must be attributed, at least in part, to the weakening of the hull as a whole by cutting away the bulkheads on which its strength depended. The loss of the Birkenhead immediately became famous as an example of discipline and heroism, and deservedly so. When the news reached Berlin, the King of Prussia ordered the story to be read aloud to all the units of his army, specially paraded for the purpose. But perhaps it would have been better still if he had instructed his War Office not to interfere with the structure of ships, a matter which soldiers do not always understand. According to Mr. K. C. Barnaby, a distinguished naval architect, the idea that open space was more important than safety in troopships lasted for many years. He says that, as late as 1882, shipowners were complaining that, when they fitted additional bulkheads as urged by the Admiralty, the trooping authorities would not accept the ships on the ground that the spaces between the bulkheads were too small. On being overweight. Almost every structure has a tendency to turn out heavier than its designer intended. This is partly due to over-optimistic estimating in the weights office, but it is also due to a tendency on the part of almost everybody to play safe by making each part just that much thicker and heavier than is really necessary. In many people's eyes this is a sort of virtue, a sign of honesty and integrity, and we talk of things being heavily built as a term of praise, while lightly built is almost synonymous with flimsy or shoddy. Sometimes this does not matter, but there are cases where it matters very much indeed. With aircraft the weight is tending to increase all the time, from the drawing board onwards. Extra weight naturally restricts the fuel capacity or the payload of the aeroplane, but, besides this increase in gross weight, the center of gravity of an aeroplane somehow always manages to work its way too far aft. In other words, the weight of the tail tends to increase out of proportion to that of the rest of the machine. This can be a serious matter. If the CG gets too far aft, the aircraft will acquire dangerous flying characteristics. It may have a tendency to go into a spin from which it is unable to recover. For this reason a surprising number of aircraft, including some very famous ones, have gone around all their lives carrying massive lead weights permanently bolted into their noses. This is necessary in order to keep the CG in a tolerably safe position. It need hardly be said that this is a bad thing. The effects of overweight are just as bad, perhaps worse, with ships. Not only do all ship hulls tend to be overweight absolutely, but the CG tends, in this case, to creep, not backwards but upwards, ineluctably upwards. Now the stability of a ship, that is, Her tendency to float right side up, instead of upside down or on her side, depends upon something called her metacentric height. This is the vertical distance between a mystic but important point called the metacenter and her center of gravity. For excellent reasons, the metacentric height of even a large ship is likely to be quite a small distance, in fact in the region of 1 or 2 feet, perhaps less. Thus the position of the CG has only to rise by a matter of a few inches to reduce the metacentric height by a very significant fraction, which may well imperil the safety of the ship. Various ships have capsized on launching for this reason, and no doubt the yard foreman, or whoever were responsible for the extra top weight, considered that they were in no way to blame. We mentioned the loss of HMS Captain in Chapter 11. The whole story of the Captain was intensely political and controversial at the time. I suppose few accidents can have had such far-reaching historical consequences. The Captain represented one turning point in the evolution of the steam battleship and perhaps in the modern concept of world power. The Admiralty have often been criticized by historians who know very little about ships for their slowness in changing from sail to steam. These are sometimes just the historians who are most critical of imperialist expansion and so forth. It has to be borne in mind that, until comparatively recently, the unreliable engines, the high coal consumption and the short range of steam warships made them dependent upon bases and coaling stations and colonies as soon as they ventured beyond home waters. The exercise of world power by steam navies is a very different sort of thing from the strategy and logistics of 18th century sailing fleets. It was basically for such reasons that the British Admiralty insisted upon the retention of full sail power, in addition to engines, in most of their battleships almost to within living memory. The technical difficulty of combining sail with steam propulsion lay less in the nature of engines and sails than in the developments which took place during the 19th century in guns and armor. Turret guns require a wide angle of fire, besides being very heavy. The necessary protective armor was even heavier. To combine the required fields of fire, and also adequate stability, with full sail propulsion constituted a very difficult problem in naval architecture. In the 1860s the Admiralty were understandably inclined to proceed cautiously. If they had been allowed to continue to do so, all might have been well and history might have been considerably different. This apple cart was upset by a certain Captain Cowper Coles. Coles was one of those clever men with an exceptional talent for controversy and publicity. Having invented a new sort of gun turret, he set himself to persuade the Admiralty to build a battleship around it with full sailing rig and therefore unlimited range. Coles managed to involve, not only the Admiralty, but also both houses of Parliament, the royal family, the editor of the Times and practically the whole of the establishment. In what became one of the greatest publicity exercises of its kind. Tiring eventually of being called reactionary by half the newspapers and more than half the politicians in the country, the Admiralty gave way. They did what they had never done before, and will certainly never do again. They allowed a serving naval officer with no qualifications in naval architecture to design his own private battleship and have her built at the public expense. The ship was built by lairds at Birkenhead as Coles's responsibility and with none of the usual checks on design. She was, moreover, built in a blaze of vituperation and controversy. For much of the time Coles himself was ill and unable to leave his home in the Isle of Wight to attend the yard. As a result of all this muddling, the ship ended up about 15% overweight. If this had not been the case, it is at least possible that the ship would have been a success and comparatively safe. As it was, the Captain was much too deep in the water and her CG was much too high up. Subsequent calculations showed that the ship would capsize if allowed to heel beyond an angle of 21 degrees. However, the ship was commissioned in 1869 with much publicity. She made 2 deep-water cruises to the great satisfaction of the Times and of the First Lord of the Admiralty, who had his own midshipman's son transferred into her. It looked as if the problems of world power, without the encumbrance and potential embarrassment of world bases, were going to continue to be soluble. On her third voyage, returning from Gibraltar in 1870 in company with the rest of the Channel Fleet, HMS Captain suddenly capsized in a rather moderate squall in the Bay of Biscay. 472 lives were lost, more than the total British dead at Trafalgar. Both Cowper Coles himself and the First Lord's son were drowned. Only 17 men and 1 officer were saved. Though not, of course, the sole factor, the loss of the captain had a powerful effect in accelerating the change from sail to steam, or rather on the abolition of the full sailing rigs in big battleships. Whatever the technical consequences, the political ones were extensive. It will be remembered that the Suez Canal, which was opened just before the Captain was launched, originally belonged effectively to France. Disraeli bought the Suez Canal shares for the British government in 1874, and the acquisition of a worldwide chain of coaling stations became a political necessity. The whole story of the Captain disaster is complicated, but the immediate technical cause was undoubtedly the determination to ensure that the masts and hull of the ship should have really adequate strength, regardless of weight. It was one of many structural accidents in which nothing actually broke, but the causes were just as structural as if they had aeroelasticity or a reed shaken by the wind. When a fluid, such as air or water, flows past an obstruction, which might be a tree or a rope, eddies of fluid are formed behind it. Quite often, if you observe a reed or a bulrush growing in a fairly slow-moving river, you will see that the eddies in the sliding water are formed first on one side, then on the other, alternately. The result is a rhythmic variation of fluid pressure, from one flank of the obstruction to the other. Such a succession or street of eddies is called a Kármánstrasse, after the aerodynamicist von Kármán, who first described it. It is often quite easy to see eddies on the surface of smooth water, though eddies in air are invisible unless they are shown up by smoke or dead leaves or some similar indicator. In fact, however, just the same Kármánstrasse of eddies happens when air blows past a flag or a tree or a wire. The result of these alternate eddies, acting first on one side then the other, is that the flag flaps, the tree sways and the telegraph wires sing and hum in the wind. Thus a sail will flap as soon as the sheet is eased and may very well split itself or injure somebody. I remember seeing a man knocked out by a flogging sheet block. There is a lot of energy involved. When a big ship is tacking in a breeze, the noise is as loud as gunfire and much more impressive. If the frequency of the aerodynamic stimulus provided by the eddies happens to coincide with one of the natural periods of vibration of the obstruction, then the amplitude of the movement may increase until something breaks. It is this sort of thing, rather than steady wind pressure, which usually accounts for trees being blown down. In a somewhat more sophisticated way, this is also what is rather too apt to happen with aeroplanes and suspension bridges. It can be prevented by making the structure adequately stiff, especially in torsion. As we have already remarked, it is the torsional stiffness requirements which generally govern the design, and the structure weight, of modern aircraft. Although Telford's Menai suspension bridge was quite badly damaged by wind-induced oscillations not long after it was built, it took about a century for the reality of this danger to register properly with bridge designers. The classic catastrophe was that of the Tacoma Narrows Bridge in America in 1940. This bridge, which had a span of 2,800 feet, 840 meters, was built without adequate torsional stiffness. As a result, it swayed in even a moderate breeze to such an extent that the locals immediately christened it Galloping Gertie. Quite soon after it was built, it swayed and wriggled itself into a dramatic collapse in a wind of only 42 miles per hour. Fortunately, somebody happened to be present with a film in their cinecamera. The camera worked, and the price of the film must have turned out to be a good investment, since it has been shown repeatedly in practically every engineering school in the world ever since. Plate 20. In consequence, modern suspension bridges are built with adequate stiffness, especially torsional stiffness. As in aircraft, the stiffness requirements account for a good proportion of the weight of the bridge. In the case of the 7-road bridge, plate 12, for instance, the decking is made from a very large steel tube of flattish 6-sided section, built up from mild steel plates. During construction, this tube was floated out in sections, which were hoisted into place and then welded into a continuous structure. Engineering design as applied theology. In nearly all accidents we need to distinguish two different levels of causation. The first is the immediate technical or mechanical reason for the accident, the second is the underlying human reason. It is quite true that design is not a very precise business, that unexpected things happen, that genuine mistakes are made and so forth, but much more often the real reason for an accident is preventable human error. It is rather fashionable at present to assume that error is one of those tilings for which it is not really fair to blame people, who, after all, were doing their best or are the victims of their upbringing and environment, or the social system, and so on and so on. But error shades off into what it is now very unpopular to call sin. In the course of a long professional life spent, or misspent, in the study of the strength of materials and structures, I have had cause to examine a lot of accidents. Many of them fatal. I have been forced to the conclusion that very few accidents just happen in a morally neutral way. 9 out of 10 accidents are caused, not by more or less abstruse technical effects, but by old-fashioned human sin, often verging on plain wickedness. Of course, I do not mean the more gilded and juicy sins like deliberate murder, large-scale fraud, or sex. It is squalid sins like carelessness, idleness. One T learn and don't need to ask, you can't tell me anything about my job, pride, jealousy and greed that kill people. Though some engineering firms have splendid design teams, far too many firms in this country are technically incompetent, often to a criminal extent. Many of these people have risen from the shop floor, and, out of a mixture of pride and meanness, they intensely resent any suggestion that they should seek proper advice or employ qualified staff. It is my experience that far more accidents occur every week than ever get into the papers. Generally they are caused by lack of proper care and professional competence. I very much doubt if the remedy lies in the imposition of yet more regulations. It seems to me that what is wanted is the creation of more public awareness and a climate of opinion which regards such mistakes as morally culpable. The man who drilled a hole in the wrong place in the wing spar of a wooden aeroplane, plugged the hole, and said nothing, was acquitted. Presumably the jury thought that the moral blame was negligible. What is wanted is much more publicity. The difficulty lies in the law of libel. In most cases, if the real causes of an accident are made public, somebody's face will be very red, and it is likely that their business or professional reputation will suffer. Most practicing engineers are acutely aware of this and have to keep quiet or risk heavy damages. In my opinion, there should be some way round this, for it is in the public interest that accidents and blunders should be publicized. Though the great majority of structural accidents are sordid backstreet affairs which we hear very little about, there are, of course, a certain number of great dramatic accidents which, for a while, monopolized the headlines. Of such a kind were the Tay Bridge collapse in 1879, the capsize of the Captain in 1870, and the A101 disaster in 1930. These are very often intensely human and intensely political affairs, caused basically by ambition and pride. The sinking of the Captain was of this nature. The two men who carried the heaviest moral responsibility paid heavily for their faults, the one with his own life, the other with that of his son. Unfortunately, a great many other lives were lost too. The wreck of the airship A101, which hit the ground and was burnt out at Beauvais in 1930, was basically similar. There is a splendid account of this by Neville Shute in his book Slide Rule. The immediate technical cause of the accident was the tearing of the fabric of the outer envelope. This fabric had apparently been embrittled by improper doping treatment. The real reason for the disaster was, however, pride and jealousy and political ambition. The Labour government's Air Minister, Lord Thompson, who carried the ultimate responsibility, was burnt to death in the accident, along with his valet and nearly 50 of the crew. Neville Shute's account of the events leading up to the accident corresponds extraordinarily closely in character with my own experience of rather comparable circumstances. One can at once recognize a certain atmosphere of Gadarene inevitability about the whole procedure. Under the pressure of pride and jealousy and ambition and political rivalry, attention is concentrated on the day-to-day details. The broad judgments, the generalship of engineering, end by being impossible. The whole thing becomes unstoppable and slides to disaster before one's eyes. Thus are the purposes of Zeus accomplished. People do not become immune from the classical or theological human weaknesses merely because they are operating in a technical situation, and several of these catastrophes have much of the drama and inevitability of Greek tragedy. It may be that some of our textbooks ought to be written by people like Aeschylus or Sophocles. These writers were not humanists. Arnold, 1966. Each tour of duty for an airman in Bomber Command consisted of 30 sorties or operational flights. Such service was therefore exceptionally dangerous. The loss of life in Bomber Command was comparable to that of the German U-boat crews, which was notoriously high. The extra 20% was required by the airworthiness authorities so as to cater for variations in the material and in the assembly procedures. An act of God has been defined by A. P. Herbert as that which no reasonable man would expect. Bread upon the waters, published in the day's work. She died of TB at the age of 27. What she actually did was more intelligent and much more seaman-like than one would infer from the popular stories and pictures. Except, of course, the engine room bulkheads. K. C. Barnaby, Some Ship Disasters and Their Causes, Hutchinson, 1968. Chapter 16 Efficiency and Aesthetics. Or the world we have to live in. Why don't you have Mr. Smith in your cabinet, Mr. President? I don't like his face. But the poor man can't help his face. Anybody over 40 can help their face. Told of President Lincoln. Once upon a time I used to work in an explosives laboratory. Naturally, very thorough precautions were imposed by the authorities against the entry of unauthorized persons, who not only might sell stolen explosives for a large profit, but might equally well blow the whole place up. Thus this establishment was ringed with barbed wire and alarm bells and armed guards and police dogs and with nearly every device that the ingenuity of security officers could think of. Now many practical explosives are based on nitroglycerine, which, by itself, is an exceptionally dangerous liquid both to store and to handle. The least undue familiarity, such as shaking the bottle, may cause it to detonate with the most appalling results. Ordinary safe explosives, such as dynamite, contain a large amount of nitroglycerine which is only rendered safe to handle by the addition of various substances that have been developed over the years by a succession of rather brave scientists, such as Abel and Nobel. Those who have to experiment with straight nitroglycerin need to take the most fantastic precautions, and the dangers are such that they not infrequently suffer from nervous breakdowns. Not only are nitroglycerine laboratories physically separated from other buildings by earthen embankments and wide open spaces, but the staff often wear special clothing, including a peculiar kind of boot devised so that they may tread softly and build up no electrical charges, let alone anything so dangerous as a spark. One weekend some of the local children managed to wriggle under the security fence and to evade the police and their dogs. Finding themselves in an apparently lonely place, they broke into one of the nitroglycerine laboratories. There was, however, nothing very much there to interest them, so they upset the various bottles and beakers of nitroglycerine onto the floor, stole a couple of pairs of special boots and escaped, by the way they had come, undetected from that day to this. This is a true story, but I rather think that it might also serve as some sort of parable, for it is Possible that engineers and planners and bureaucrats and do-gooders and all the company of the avant-garde are like children playing in a shed full of nitroglycerin, sublimely unaware that they may cause a major explosion. It is all very well to concentrate on efficiency and making things work, and of course, it is necessary to meet material needs, though in fact our material needs are more flexible than we like to think. However, people have subjective needs which are more important and much more likely to lead to social explosions if they are abused or neglected. So, when I listen to some of my engineering colleagues talking, I sometimes shake in my shoes. It is not only that they regard the aesthetic consequences of their work as of quite minor importance, but that they regard concern about it as basically frivolous. Yet I think that the more we increase material prosperity, the more serious in the long run will be the ultimate catastrophe if people cannot find aesthetic satisfaction. When I was an engineering student, I used to escape from my classes, panting for air, and creep guiltily to the local museum. Many a mathematical lecture did I cut, spending the time looking at the pictures in the Glasgow Art Gallery. No doubt pictures in museums do help, but in a way such things are a pathetic necessity, a refuge of desperation, not only from the aridities of analytical lectures but, more important, from the all-pervasive ugliness of towns like Glasgow. Of course it suits the tidy Philistine administrative mind to keep art in separate boxes called museums and theatres, and it is noticeable that the brave new 1984 regimes provide not only pictures in galleries but also music and ballet. But such forms of fine art can only operate occasionally in the ordinary person's life. They may provide an escape, but they are really no substitute for an environment which is satisfying in itself and is continually present. Most of us find some sort of refreshment in the countryside, but we are pretty well resigned to the dreariness of towns and factories and filling stations and airports and most of the things with which we have to spend our day. Possibly fish which have to live permanently in dirty water may get more or less used to it, but human beings who are conditioned in this way ought to rebel. We compound for sins, we are inclined to by damning those we have no mind to. And, as Professor McNeill Dixon once said, contrast the middle centuries, that unique period in our European annals, with the centuries following upon the Renaissance. How different their respective views of the world, how opposed their systems of belief. Yet in each the doctrines universally held are felt as inevitable, as unassailable. Each age thinks itself in possession of the true and only view possible for sensible man. Thus, about the important things, each age has a totally closed mind. Nowadays, being materialists, we are duly horrified that our ancestors were prepared to tolerate physical poverty and to inflict physical pain. But these same ancestors would be just as horrified that we should suffer many millions of people to experience every day the beastliness of London or New York, and that those who work in our dark satanic mills should have to be well paid to put up with noise and ugliness which are largely unnecessary. Even the clinical decor and atmosphere of modern hospitals would seem to them to add a new terror to dying. Therefore many of us seek some kind of relief or consolation in nature, and we escape, when we can, to the country, because we find the countryside more agreeable than towns and roads and factories. Many people indeed believe that nature is in some way inherently beautiful and, perhaps, in some way inherently good. Taken to the extreme, such views lead to something very like pantheism, to Meredith's Woods of Westermain. But it seems to me that, if we can only get rid of our romantic prejudices and really look at all sides of the question, we are forced to the view that nature is just as aesthetically neutral as she is morally neutral. Mountains and lakes and sunsets may be beautiful, but the sea is often menacing and ugly, and, so far as I have experienced them, primeval forests are frequently places of horror. Most of the European landscape is not really natural at all. The kinds of plants and trees which are allowed to grow have been carefully selected and controlled, and many species have been artificially bred to their present forms, just as much so as the domestic animals. The patterns in which the plants are grown, the whole layout of fields and woods Roads and hedges and villages, not to mention drainage and land improvement, are the result of human choice and effort. Before the 18th century, when most landscape was much wilder, educated men had a dread of nature, which implied to them not only physical discomfort, but pain in the raw. To these people it was the towns which were habitable and attractive, the country which was inhospitable and ugly. Today, when we admire the lovely English landscape, we are really admiring something which was deliberately created by the civilized and intelligent English 18th century landlords. If the country has gone up in the aesthetic world, the towns have certainly come down. Nowadays, when we deplore English towns and factories, we are deploring the product of Philistine reformers and engineers and architects and businessmen and the little grey men who sit in council offices and the bigger grey men who sit in Parliament. Of these people's sins, it is not enough to say that they know not what they do, for we do that which is inherent in our natures, as Plato well knew. It is at least arguable that the countryside is more attractive than the town, not because the country is more natural but because town and country were made, by and large, by very different kinds of people. But the first thing is to see ugliness for what it is rather than accepting it as part of the natural order of things. We do that which is inherent within us. In a world which has an unreasonable admiration for reason, we are apt to forget that the human mind is rather like an iceberg. The rational part of our minds, of which we are conscious, is quite small, and, like the visible part of the iceberg, it is supported from underneath by the subconscious mind, which is much larger. At this point I am only too acutely aware that we are reaching a stage in the argument which is the province of artists and philosophers and psychologists, and that I am miserably qualified to blunder into regions where the angels of art criticism fear to tread. I can only plead that necessity knows no laws, that the modern man-made world is hideous, that sheer desperation induces me, a naval architect manque, to stick my neck out. I think it is really important that some sort of view of the aesthetics of technology and engineering and structures should be put forward to engineers and technologists by one of themselves, however inadequate that view may be. For what follows I commit myself to Athena and to Apollo. By their grace may somebody more competent than myself be provoked into doing the job better. Let us begin by looking at the human reception process in aesthetics, that is to say, why we react as we do to some inanimate object. Within the subconscious mind there lies an enormous store of potential reactions and forgotten memories. This material is partly inherited genetically from a remote past, Jung's collective unconscious, and partly acquired by the individual himself during the course of his own life, mainly from apparently forgotten experiences, sometimes unpleasant ones. Now our physical senses, sight, hearing, smell and touch, continually pass to our brains far more information about our surroundings than our conscious mind can accept or be aware of. But the subconscious is monitoring this information all the time, and it is full of receptors and tripwires which are liable to be influenced by every shape and every line, every color and every smell, every texture and every sound. We may be totally unconscious of this, but it is happening all the same, and it is building up subjective emotional experiences within us, be the effects good or bad. This sort of process may account in some measure for the way in which we are influenced, subjectively, by inanimate objects, and especially in the present context by artifacts. Artifacts are made by people, and somebody, at some stage, has some sort of choice in the shape and the design. It is impossible to make any object without making a series of statements in the process. Even a straight line is saying in effect, look, I am straight, not crooked. Even a very simple artifact contains a package of such statements which have been made by people. Just as there can be no such thing as a totally objective experience, so there can be no such thing as a totally objective statement, one with no emotional connotations of any kind. This is true whether the statement be made in words or music or color or shape or line or texture, or in what engineers call design. This brings us from what might be called the aesthetic reception process to the aesthetic transmission process. In other words, how do things come to be designed as they are? What is it that the maker or the designer puts into an artifact which causes it to have the aesthetic effects which it does? The short answer is, to a large extent, his own character and his own values. Thus whatever we make and whatever we do, we nearly always leave upon the thing or upon the action the imprint of our personalities, written in a code which can usually only be read at the subconscious level. For instance, our voices, our handwriting, and our manner of walking are quite characteristic and are usually difficult to disguise or to imitate. But this sort of thing extends much further than these familiar examples. One dark evening I was in a yacht anchored in a remote Scottish loch. Round the corner of the land, 3 or 4 miles away, there came another sailing yacht which I had never seen before and of which I had no knowledge. Though it was quite impossible to recognize her name or her crew, I said to my wife, "That boat is being sailed by Professor Thorne." And so she was, for the way in which a man sails a ship to windward is quite as individual as his voice or his writing, and, once seen, can hardly be forgotten. In the same way one can often tell which of one's friends is flying a light aircraft, for the manner of flying shows, unmistakably, the imprint of the character. In the field of painting and drawing, even the work of very amateur performers is apt to tell one more about themselves than about their subjects. Again, it requires exceptional skill to imitate really plausibly the work of a particular artist. Naturally, there is no sharp line between painting and drawing and technological design, and almost everything that gets made is likely to carry with it something of the personality of the maker. What is true of individuals is also apt to be true of a society, a culture, or an age. Archaeologists can usually date artifacts, such as potsherds, within a very few years on stylistic grounds. If you walk around Pompeii and Herculaneum, you will come away with a quite surprisingly powerful sense of what sort of people the inhabitants were. This has little or nothing to do with the technology of things like the plumbing, and it is something which no amount of factual history can convey. So far this sort of pattern recognition has eluded the computer. Long may it continue to do so. Recently, I was drinking canned beer with a much respected colleague. I said, rather unwisely and priggishly, "I suppose really a thing like this beer can seems to me to epitomize all the dreariness and commercialism that is wrong with technology nowadays." My much respected colleague was down on me like a ton of bricks. "I suppose you want to sell beer in pitchers or wooden barrels or wine skins or something. What else would you sell beer in this day and age except tin cans? How stupid and impractical and reactionary can you be?" But, with respect, my much respected colleague was missing the whole point. It is not what you do but how you do it that matters. Beer containers are not beautiful or ugly because of the material from which they are made, or even because they are mass-produced. Whatever they are made out of, they will convey, unavoidably, the values of the people who are responsible for them. We happen to be a society which is unable to make attractive beer cans. Indeed we are, I fear, an age rather noticeably lacking in inherent grace and charm. Greek amphorae were beautiful, not because they held wine and were made of clay, but because the Greeks made them. They were, in their day, simply the cheapest containers for wine. If the Greeks had made tin beer cans, perhaps we should now have collections of classical beer cans in museums, much admired by artists. I believe that very few artifacts are intrinsically ugly or beautiful simply because of their function *, they are rather mirrors to an age, to a set of values. Rather the same conditions obtained during the 18th century as in ancient Greece, partly no doubt because it was a classical age which consciously modelled itself on the ancient world. Nearly everything the 18th century craftsmen touched was elegant. This was not just a matter of the luxury trade, it extended right through society. Of course, this begs the whole question of absolute standards in aesthetics. Are not my values as good as yours, however deplorable and uneducated you may consider my taste to be? Well, I for one feel strongly that there are absolute standards in aesthetics which change only gradually through the ages. The modern fashion for aesthetic democracy seems to me perverse and nihilistic and based largely on a desire to bash the establishment. I would take the view that there is a continuing tradition of values in aesthetics, just as there is in ethics. The process is an iterative one, advancing slowly and painfully from age to age and from fashion to fashion, building, like science, on the experience of the past. Otherwise, how are civilized values ever to be built up? Another debatable point is granted that common objects such as Greek amphorae were beautiful in some absolute sense. Did the Greeks realize that they were beautiful? I am reminded of a remark in a leading article in the Times, which said something like good typography should be like clean glass, one should be able to see through it without being distracted. But if this is to happen, then the typography must have that sort of discreet elegance and beauty which draws no attention to itself. I think this is why we only come to appreciate many common artifacts after they have passed out of common daily use. This does not mean that they are not absolutely and permanently beautiful. And the 18th century invented the Industrial Revolution. I think it is important to point out that many of the fathers of the Industrial Revolution were not Philistines but sensitive men of considerable taste. Of such a kind were Matthew Boulton, 1728–1809, and Josiah Wedgwood, 1730–95. They made a great deal of money, the things they made were beautiful, and these two at least were model employers. No doubt there were black sheep, but the evils of the Industrial Revolution did not lie in the ethic of 18th century culture and classicism but rather in a newly arisen vulgarity and greed which came, I think, from outside this ethic. Neither mass production machinery itself nor its products are intrinsically ugly. The very first real mass production machinery, the well-known block-making equipment installed around 1800 at Portsmouth Dockyard by Sir Mark Brunei, is handsome and satisfying. These machines were not only good-looking but also verve effective, for they turned out automatically all the millions of pulley blocks needed by the sailing navy during the Napoleonic Wars and for long afterwards. They saved a vast amount of money in doing so, for blocks are expensive things and a single warship might require 1,500 of them. Some of this machinery can now be seen in the Science Museum, Plate 21, but a good deal of it is still in service at Portsmouth after 180 years, supplying the modern Navy's diminished need for blocks. Not only the machinery but the product, the blocks themselves, is solid and handsome. Whether you would call a block beautiful is a matter of opinion, but they are certainly pleasant to look at. Sir Mark, father of the great Isambard Kingdom Brunei, was a French royalist émigré, and all accounts agree that he was a charming man. We are told that the dear old man had, with a great deal more warmth than belonged to that school, the manner, bearing, and address and even the dress of a French gentleman of the ancient regime, for he had kept to a rather antiquated but very becoming costume. I was perfectly charmed with him at our first meeting. What I loved in old Brunei was his expansive taste and his love or ardent sympathy for things he did not understand or had not had time to learn. What I most admired of all was his thorough simplicity and unworldliness of character, his indifference to mere lucre, and his genuine absent-mindedness. Evidently he had lived as if there were no rogues in the world. No doubt a very impractical sort of character who would find difficulty in getting a job with a modern go-ahead firm. But his machinery is still producing blocks, nearly 200 years after he made it, and it is beautiful. The great engineers who worked before and immediately after 1800 between them laid the foundations, not only of British industrial prosperity, but of the modern technological world. Many of these people were men of taste. But by the time Queen Victoria came to the throne, public taste was undoubtedly deteriorating. By 1851 it had reached an all-time low. Shrewd observers, like Lord Playfair, 1818–98, were, however, already remarking, as early as the time of the Great Exhibition, that British industry was losing its impetus and its creativity. Although it is very widely and commonly believed, indeed taken as axiomatic, that ugliness came in with industrialism as an inescapable consequence of mass production, I doubt if this view would really stand up to proper historical examination. I think it is more reasonable to suppose that elegance and business enterprise declined more or less hand in hand and as a result of something rather nasty and complacent which emerged from the British character during the Age of Reform. The passionate protest of the aesthetic movement in the 1870s and 1880s against the ugliness of pretty well everything failed to have much effect. I think this was less because these people were guyed by Gilbert and Sullivan in Patience and in the pages of Punch than because the movement was largely an escapist one and attacked the wrong targets. These sons of Mary failed to see that the root cause of all the brazen horrors which they hated so much lay, not in machinery itself, but in attitudes of mind. Like so many aesthetic reformers, they rejected technology instead of joining it. Perhaps if they had been prepared to learn technology and engineering they might have operated from within the system. But this is a laborious discipline which too many arts people reject as being somehow beneath them. Of course William Morris and his followers studied and practiced various small-scale technical crafts, but what was needed was to come to terms with real mass-production machinery and with the economic problems of a high-production society. On efficiency and functionalism. But when his disciples saw it they had indignation, saying, "To what purpose is this waste? For this ointment might have been sold for much, and given to the poor." Matthew 26:8-9. Although we may justly accuse modern engineers of Philistinism, nearly all of them do cling to certain very important values which are unfashionable and unpopular in a permissive age. The chief of these are objectivity and responsibility. Engineers have to deal, not only with people and all their quirks and weaknesses, but also with physical facts. One can sometimes argue with people, and it is not difficult to deceive them, but it is of no use to argue with a physical fact. One cannot bully it or bribe it or legislate against it or pretend that the truth is something different or that the thing never happened at all. Laymen and politicians may create what fantasies they choose, but, for the engineers, it is their care that the gear engages, it is their care that the switches lock. Essentially, these people's stuff must work, and go on working, safely and economically. It may be the engineer's job to point out that the emperor has no clothes on, but however embarrassing this may be, we clearly need more, not less, of this kind of realism. In the pursuit of their objective profession, engineers have developed a number of concepts which are useful as aids to realism. One of these is efficiency. Thus it is very helpful to know what fraction of the expensive energy which is fed into an engine as fuel emerges as useful power. This can be expressed as a simple ratio or percentage, and it tells us a most important fact about one aspect of the working of the engine. Again, it is valuable to be able to compare the weights and costs and load-carrying capacities of various kinds of structures. As we saw in Chapter 14, there are various numerical ways of doing this. But the concept of efficiency is so useful, and sometimes so economically powerful, that there is a danger of being carried away by it. If we try to apply the idea of efficiency to the totality of a situation, then we are usually presuming to a wisdom, to a knowledge of all the facts, which is most unlikely in mortal man. We may fairly talk of the efficiency of an engine in terms of fuel consumption and power output. If we talk of the efficiency of the engine, tout court, we are being hubristic. We take no account, for instance, of the noise and smell which the engine makes, or whether the man who has to start it is likely to have heart failure, or how much pleasure anybody derives from its appearance. Even if we know all the relevant facts about any technological situation, which is impossible, we could not weight them or quantify them, for many of them are incommensurable. Not long ago there was a great to-do about the proposal to build a vast airport on the Essex coast. This was a project to put down a hideous mass of concrete and sheds and machinery upon the wet, ribbed sands of the Thames estuary, where the gulls paddle and wheel and squawk. The politicians and the administrators and the economists and the engineers were full of facts and figures about the need for another airport. But it is impossible by any numerical criterion to compare the claims of the planners and the economists with the rights of the gulls and with the beauty of the wet sands. For myself, I am passionately on the side of the gulls, and it gives me immense pleasure to think of all those miles of wet sand and mud, which, I am glad to say, is quite useless and unproductive. So far, the gulls and the sands seem to be winning. I suppose that it is possible to measure the efficiency of an airport in terms of how many aircraft and passengers it can handle in relation to the capital costs and running costs, and these figures have some practical value, even if they bear no relation in this world to seagulls and wet sand. But for many things the concept of efficiency is simply irrelevant. It is meaningless to talk about the efficiency of a piece of furniture or of a cathedral. All the same, engineers cling to the idea that it ought to be possible in some way to measure the efficiency of practically everything. But this is nonsense. Very well, says the engineer, but things must be functional. The beauty of technology lies in its functionalism. If by this he means that things must work and do their job properly, then he is merely stating the obvious. But when we come to apply functionalism as an aesthetic criterion, we are apt to get into some very deep water. There are certain structures, such as bridges, where the structural function is simple and obvious and proclaims itself as such. Many of these are beautiful, but some of them are not. There are also a certain number of very expensive artifacts which are certainly good-looking, such as Concorde and the Rolls-Royce car. But are we sure that we are not admiring perfection of workmanship, purchased almost regardless of cost? Ought we not to take cost into account in assessing functionalism? Now a Ford car can be bought for something like a tenth of the cost of a Rolls, and in the real world, where things have to be paid for, many people would regard the Ford as more functional than the Rolls. But the external appearance of the Ford bears little relation to its mechanical workings. What we see is more or less a tin box put round the machinery by the bodymakers and the stylists. The mechanical, that is to say, the functional, parts of any modern mass-produced car are not attractive, being made largely from bits of wire and bent metal which we find it difficult to admire, however useful they may be. In the same sort of way, most electrical devices such as wireless sets are hideous in their naked wiry state, and we are constrained to hide them inside black or grey or walnut boxes. On the whole, it may be fair to say that, as modern technology gets more and more functional, we can less and less bear to look at it. But have we not good precedents in nature? The outside of a person or an animal may be very beautiful, the inside is generally repulsive. Our admiration of nature is highly selective. We admire certain stages of growth, lambs but not fetuses. We are generally horrified by decay and all those worms. But decay is just as necessary and just as functional as growth. With regard to this question of functionalism and efficiency, nature seems to have a sense of humor, or perhaps just a sense of proportion. She will construct the stem of a plant, for instance, with the uttermost regard for metabolic economy. The thing is a miracle of structural efficiency. Having done this, she will put a great big flower on top, for fun, as far as one can see. In the same way, peacocks have tails and gulls have hair which cannot be considered strictly functional. If it be urged by some dreary person that these things are done to encourage reproduction, this is only putting the argument back by one notch. For why should these ornaments be attractive, sexually or otherwise? Although it is practically an article of religion with many engineers to believe in a close connection between functional efficiency and appearance, I am, myself, skeptical. Of course, the grossly ineffectual will, and should, offend the eye, but I doubt if the refinements of technical performance really improve appearance very much. Very often it is the other way round. The pursuit of the last ounce of performance results in a boring appearance, as one can see in modern yachts. 4. Myself, I stick to the belief that what one gets aesthetically from an artifact is some combination of the personality of the maker with the accepted values of usage. If you walk down any street with your eyes and your mind open, you can form your own judgment on both. Science has been attacked on almost every conceivable ground ever since the Renaissance. Most of these attacks were more or less rubbish. But it is always strange to me that what seems the real argument against science is seldom raised, at least in a direct form. This is that science has subtly warped our system of values by teaching us to judge on grounds which are excessively functional. The modern man asks, what is this man or this thing for, rather than what is this man or this thing? Herein, no doubt, lie the causes of many of our modern sicknesses. The aesthetic judgment seeks, however inadequately, to answer the broader and the more important question. Too often, nowadays our subjective judgment clashes with our scientific, or Banalsic, judgment. But we sweep the aesthetic judgment under the carpet at our peril. Naturally, there is nothing in all this to prevent a beautiful object from also being an efficient one. The point I am making is that the two qualities are what the mathematician would call independent variables. I am reminded of the Irish yachtsman's remark, an ugly ship is no more attractive than an ugly woman, however fast she may be. On formalism and stresses. Modern art and architecture make a great parade about their freedom from traditional forms and conventions, which is possibly why they have achieved so little. Yet formality in design or in manners is not a handicap. Such conventions protect the weak and aid the strong. All the loveliest ships have been designed within a stylistic tradition, and I cannot imagine that their designers felt cramped by it. The Greek dramatists wrote within a strict set of rules, but it would be as absurd to think that the Antigone is limited by the dramatic unities as to suppose that Jane Austen would somehow have been able to produce greater masterpieces if she had felt free to make use of bad language and overt sex. Of course, fully to appreciate formal achievement it is necessary to have some knowledge of the rules. This applies just as much to the appreciation of cathedrals and bridges and ships as it does to watching cricket. This provides one good reason for knowing something about the principles of engineering as well as the history of art and architecture. When Ictinus designed the Parthenon in 446 BC, he worked within the well-established Doric order of architecture. The Parthenon, the Temple of the Maiden, is indisputably one of the most beautiful buildings in the world, possibly the greatest of all artifacts. Although it is dedicated to the divine Athena, it is, to me, the supreme statement of humanism, of what the scientist Humphrey Davy called the brilliant but delusive dreams concerning the infinite improvability of man. Furthermore, it was built at the very peak of Athenian power and glory, and it speaks of the city of the Maiden. Rich and renowned and violet-crowned, Athens the envied of nations. Nemesis, of course, lay just around the corner, very much as it did in 1914. When it was new, in all its white marble, red and blue paint and gilded bronze, the Parthenon might have been just a little vulgar, like some of Kipling. But is not great art always a little vulgar? If the Parthenon is a monument of humanism, some of the earlier Doric temples, say those of Paestum, seem to me to express a moving religious feeling. Contrariwise, the temple of Hephaestos in Athens, I think, conveys very little, except a faint whiff of commercialism, like Birmingham Town Hall. Yet all these different effects were produced by architects working within a single rigid language. As with all great art, there are many ways of interpreting the Parthenon. What is beyond argument is the magnitude of the achievement. But how did Ictinus do it, working as he did within a strict stylistic convention? Naturally, only one man really knew the answers, and that was Ictinus himself. He wrote a book about it, which is now lost. We can, however, make some rather crude analytical observations. In the traditional, formal steam yacht, grace and majesty are produced by extreme delicacy and subtlety and harmony in the curves of the hull and the sweep of the shear, by the exact and loving placing of masts and funnel and superstructure, Plate 22. Mutatis mutandis, this is like the exact and loving placing of words in writing. Ship design differs from the creation of poetry only in its numeric content. So again in Doric architecture, it is the loving attention to detail which is important. Although it appears to be rectangular, there is scarcely a straight line in the Parthenon, and few lines are truly parallel. The 72 columns are inclined towards each other in such a way that, if produced, they would all meet at a single point, about 5 miles up in the sky. The eye, which expects a simple box-like structure, is deceived and enchanted by subtlety after subtlety. Like a clever woman, the Parthenon influences us and bewitches us, though we are scarcely aware of how it is done, or even that it is happening at all. Plate 23. But what has all this to do with stresses? In one sense a great deal, in another very little. As long ago as the 17th century, Fenelon observed that classical architecture owes its effects to the fact that it appears to be heavier than it really is, Gothic to the fact that it appears to be lighter than is really the case. In this respect there appears to be no aesthetic payoff from honest functionalism, from appearing to be just as heavy as you really are. The classical orders, especially Doric, appear almost to stagger under the burden of their own weight. In fact there is really very little load in most of the columns, but the swelling or entasis asterisk, which is given to them, provides a sort of Poisson's ratio effect to convince us that they are bulging. Under the compressive stress, this bulging effect is carried still further by the swelling, cushion-like capitals or echinoi which transmit the compressive load from the lintels to the heads of the columns. The effect of weight is enhanced still further by the excessive depth of the architraves. Although classical architecture operates on the emotions, at least in part through a subjective sense of stress, its beauty has little or nothing to do with modern ideas of structural efficiency, in the sense of the one-horse shay. All these buildings were, in fact, thoroughly inefficient. The compressive stresses were absurdly low, while the tensile stresses in the lintels were far too high, often dangerously so. Chapter 9. The roofs of classical buildings, as we have seen, can only be described as a structural mess. But there is nothing wrong with most of these buildings aesthetically. When we come to consider Gothic architecture, the compressive stresses in the masonry are, as a rule, a good deal higher than they are in classical buildings, and the structure as a whole is generally more stable, in spite of its aerifery appearance. The effect of lightness is, however, achieved, in part, by the use of pointed arches, which, again, are inefficient. These Gothic structures are, to the modern functional mind, excessively complicated. The real heroes of Gothic cathedrals seem to be the statues, whose weight, perched on pinnacles and flying buttresses, keeps the thrust lines stable. Chapter 9. Structurally inefficient as ancient buildings may have been, it does seem that the eye requires some subjective sense of stress if it is to find satisfaction in looking at a structure. In many modern buildings the load-bearing structure, which is often of reinforced concrete, is hidden away inside the building. All that the external observer can see is a curtain wall or cladding of thin brick or glass which is obviously inadequate to carry any load at all. I do not think I am alone in finding these buildings unsatisfactory to look at and often downright ugly. But supposing that we had some kind of structure whose means of support were clearly visible, and which was also highly efficient in the modern manner, what might we expect it to look like? Clearly this is a subject about which one could argue for a long time. However, if we may judge from the structures which are employed for landing on the moon, in which weight has been saved regardless of cost, the ultimate in one-horse shays, the answer seems likely to be hideously ugly. On skymorphs, fakes, and ornament. The earliest surviving buildings of consequence in Greece are Mycenaean and date perhaps from some time before 1500 BC. These buildings were made of stone and seem to have been deliberately and intelligently designed as structures suited to the characteristics of that material. The Mycenaeans were well aware, for instance, of the danger of excessive tensile stresses in stone lintels, and they made adequate provision to relieve the bending loads on their stone beams, as one can see in the Lion Gate at Mycenae, Plate 24. To this extent, at least, Mycenaean architecture can be described as structurally functional. When the Mycenaean civilization collapsed, around 1400 BC, Greece seems to have reverted to a dark and illiterate age, from which no buildings of any importance survive. No doubt people lived and worshipped in wooden huts of one kind or another. When formal architecture began to revive in early archaic times, perhaps about 800 BC, the early temples were built of wood, like the New England churches. Naturally, none of the original wooden temples has survived. However, the transition from wood to stone construction seems to have been a piecemeal process. As timber became scarce, decayed wooden members were replaced by stone copies. Pausanias speaks of a temple still existing at Olympia in the 2nd century AD in which some of the wooden columns still remained, mixed with more recent stone ones. Doric architecture is thus trabeate or beam architecture, based on wooden construction, and even when temples came to be built, de novo, entirely of stone, architects still stuck to the forms and proportions which were suited to timber. Not only did classical architects of the sophisticated 5th century use weak stone beams in the place of wooden lintels, they went to the trouble of copying in marble all sorts of irrelevant constructional details, such as the ends of the wooden pegs which had once held the wooden buildings together. The result ought to have been ridiculous, but it was not. It was gloriously and triumphantly successful and has served as a model for the civilized world, on and off, for 2,000 years. Survivals of this sort are known as skymorphs, shadow shapes, and in one form or another they are very common in technology. A modern instance is the survival of timber graining on the surfaces of plastic moldings and furniture. Contrary to the whole ethic of the functionalist school of engineering aesthetic thought, skymorphs are not necessarily shoddy or vulgar. Nowadays, of course, they very often are, but surely this is because of our own faulty execution, not because there is something inherently wrong with the idea. The development of the Watson steam yacht is a splendid example of a successful skymorph. The classical form for large steam yachts was evolved in latish Victorian times by the greatest of all yacht designers, G.L. Watson, who had for his epitaph justice to the line and equity to the plummet. 4. His fully powered vessels Watson retained, not only the graceful clipper bow of the sailing ship, but also the now functionless bowsprit. The result is one of the most beautiful ship conventions which has ever been developed, Plate 22. If all this be so, what are we to think about honesty in design? Honesty compels me to say not much. If skymorphs are permissible in Greek temples and steam yachts, what are we to think of the total fake? Is there any reason why we should not dress up suspension bridges as medieval castles? Motor cars to look like stagecoaches, or yew trees to look like peacocks? Personally, I am rather in favor of it. After all, the results could hardly look worse or more depressing than the results of modern functionalism, and they might be a lot more fun. What is wrong with 18th century Gothic buildings? The best of them are tremendous fun and perfectly lovely. Horace Walpole was no fool, and the Pavilion at Brighton is a delight. There are those who moan about meaningless ornament, but the phrase is surely an oxymoron, for no ornament can be meaningless, even if it means something pretty frightful. If the critic wants to imply ornament which is unsuitable or unrelated to its substrate, that is fair enough, but all ornament must have some effect. It seems to me that what we want is more, not less ornament. The truth seems to be that we are frightened to express ourselves in ornament. We don't know how to handle it, and fear that we may expose the nakedness of our mean little souls. Medieval masons did not have that kind of inhibition, and they were probably psychologically healthier in consequence. Is it not fair to ask the technologist, not only to provide artifacts which work, but also to provide beauty, even in the common street, and, above all, to provide fun? Otherwise technology will die of boredom. Let us have lots of ornament. Let there be figureheads on ships, gilded rosettes on the spandrels of bridges, statues on buildings, crinolines on women, and, everywhere, lots and lots of flags. Since we have created a whole menagerie full of new artifacts, motor cars, refrigerators, wireless sets and the Lord knows what, let us sit down and think what fun we can have in devising new kinds of decorations for them. *W. M. Dixon, The Human Situation, Penguin, 1958. *Vide the recent vogue for collecting chamber pots. Aristophanes regarded Greek oil bottles as essentially ridiculous, but he never implied that they were ugly. Indeed, the ones in museums are much admired. Appendix 1 Handbooks and Formulae. Over the last 150 years, the theoretical elasticians have analyzed the stresses and deflections in structures of almost every conceivable shape when subjected to all sorts and conditions of loads. This is all very well, but usually the results, in the raw form as published by these people, are too mathematical and too complicated to be of much direct use to ordinary human beings who are in a hurry to design something fairly simple. Fortunately, a great deal of this information has been reduced to a set of standard cases or examples, the answers to which can be expressed in the form of quite simple formulae. Formulae of this sort, covering almost any possible structural contingency, are to be found in handbooks, notably J. Rourke's Formulas for Stress and Strain, McGraw-Hill. These formulae can be used by people like you and me equipped with little more than common sense, a knowledge of elementary algebra, and the contents of Chapter 3. A few of these formulae are given in Appendixes 2 and 3 which follow. Used with caution, such formulae really are very useful indeed, and indeed they form the professional stock in trade of most engineering designers and draftsmen. There is not the slightest need to be ashamed of using them, in fact we all do. But they must be used with caution. 1. Make sure that you really understand what the formula is about. 2. Make sure that it really does apply to your particular case. 3. Remember that these formulae take no account of stress concentrations or other special local conditions. After this, plug the appropriate loads and dimensions into the formula, making sure that the units are consistent and that the noughts are right. Then do a little elementary arithmetic and out will drop a figure representing a stress or a deflection. Now look at this figure with a nasty suspicious eye and think if it looks and feels right. In any case, you had better check your arithmetic. Are you sure that you haven't dropped a 2? Naturally, neither mathematics nor handbook formulae will design a structure for us. We have to do the designing ourselves in the light of such experience and wisdom and intuition as we may possess. When we have done this, the calculations will analyze the design for us and tell us, at least approximately, what stresses and deflections to expect. In practice, therefore, design procedure often runs something like this. First, one determines the greatest loads to which the structure may be subjected and the deflections which can be allowed. Both of these are sometimes laid down by existing rules and regulations, but, where this is not the case, they may not be particularly easy to determine. This sort of thing calls for judgment, and in case of doubt it is clearly better to err on the conservative side, although, as we have seen, it is quite possible to go too far and incur danger from too much weight in the wrong places. When the loading conditions have been determined, we can sketch out, to scale, a rough design. Designers often use pads of squared paper for their preliminary sketches, and we can then apply the appropriate formulae to see what the stresses and deflections are going to look like. At the first shot these will probably be too high or too low, and so we go on modifying our sketches until they seem about right. When all this has been done, proper drawings may have to be made from which the thing can be manufactured. Formal engineering drawings are very necessary when components have to be made by the usual industrial procedures, but they are troublesome to make and may not be needed for simple jobs or amateur work. For anything of a commercial and potentially dangerous nature, however, it is my experience that a firm can look remarkably silly in a court of law if the only drawing they can produce is a sketch on the back of an envelope. When you have got as far as a working drawing, if the structure you propose to have made is an important one, the next thing to do, and a very right and proper thing, is to worry about it like blazes. When I was concerned with the introduction of plastic components into aircraft, I used to lie awake night after night worrying about them, and I attribute the fact that none of these components ever gave trouble almost entirely to the beneficent effects of worry. It is confidence that causes accidents and worry which prevents them. So go over your sums not once or twice but again and again and again. Appendix 2 Beam Theory. The basic formula for the stress S at a point P distant y from the neutral axis of a beam is so. Figure 1. Where's equals tensile or compressive stress, PSI, NM2 etc. Y equals distance from neutral axis, inches or meters, I equals second moment of area of cross-section about the neutral axis, inches 4 or meters 4, E equals Young's modulus, PSI, NM2 etc. A equals radius of curvatures of the beam at the section under consideration due to the elastic deflection set up by the bending moment m in inch pounds, Newton meters etc. Position of neutral axis. The neutral axis, NA, will always pass through the centroid, center of gravity, of the cross-section. For symmetrical sections, such as rectangles, tubes, T-sections etc., the centroid will be in the middle or center of symmetry. For other sections, it can be calculated by mathematical methods. For some simple asymmetrical sections, e.g. railway lines, one can determine the centroid accurately enough by balancing a cardboard model of the section on a pin. For more elaborate structures, such as ships' hulls, the position of the neutral axis really will have to be calculated by shear arithmetic. I. The second moment of area of a cross-section. This is often, though incorrectly, called the moment of inertia. Thus, if an element, at the point P, distant y from the neutral axis, has a cross-sectional area A, say, then the second moment of area of this element about the neutral axis will be A2. Figure 2. Thus the total I or second moment of area of the cross-section is the sum of all such elements, i.e. For irregular sections this can be calculated by arithmetic, or there is a version of Simpson's rule which gives the answer. For simple symmetrical sections, for a rectangle about the neutral axis. Figure 3. For a circle about the neutral axis. Figured 4. Thus simple box and H sections as well as hollow tubes can be calculated by subtraction. For a thin wall tube of wall thickness T, however, I equals or 3T. Figure 5. The is of a great many standard sections can be looked up in reference books. Radius of gyration, K. For some purposes, it is useful to know the value of what is called the radius of gyration of a beam section, that is to say, the distance from the neutral axis at which the area of the cross-section may be considered as acting, i.e. I equals AK2 where A equals total area of cross-section K equals radius of gyration for a rectangle, see above, K equals 0 times 289d for a circle, see above, K equals 0 times 5R for a thin-walled annulus K equals 0 times 707R. Some stock beam situations cantilevers 1. Point load W at end condition at distance x from end of beam, M equals Wx max M equals WL at B deflection at x is max deflection at A. Figure 6. 2. Uniformly distributed load W equals WL. Deflection at x is max deflection at tip. Figure 7. Simply supported beams 3. Simply supported beam with load in center bending moment map point x. Deflection y at x. Figure 8. 4. Simply supported beam with single point load not in center bending moment m at point x. Max deflection at when A, B. Figure 9. 5. Simply supported beam with uniform load. W equals WL at point x. Max deflection at center. Figure 10. FORFURTHERINFORMATON, SEEROARK, J, FORMULAS for RSTRESSANDSTIIN, MCGRAWHILL. CURRENTEDITON. Appendix 3 Torsion. Torsion. For a parallel bar or prism or tube under torsion, the twist or angular deflection theta, in radians, is given by where equals angle of twist in radians, T equals torque in inch-pounds or Newton-meters, L equals length of member subject to torsion, inches or meters, G equals shear modulus, Chapter 12, nm2 or psi. K is a factor to be found from the following table. Section K max shear stress N. Solid cylinder radius are 1/2 r4, at surface. Hollow tube radii are 1 and r2 1/2 r, r1 4 r2 4, at outer surface. Hollow tube longitudinally slit, i.e. C-section, wall thickness T, mean radius r. RT3. Any continuous thin-walled tube of thickness T, perimeter U, and enclosed area A. Again, considerably more detailed information is to be found in Rourke. Appendix for the efficiency of columns and panels under. Compression loads. For a column. Assuming that the column is of such proportions that it is liable to fail by elastic buckling, Chapter 13, then the critical or Euler load P is given by where E equals Young's modulus, I equals second moment of area of cross-section, L equals length. Now suppose the column to have a cross-section which can be expanded or contracted while remaining geometrically similar so that its size is characterized by a dimension T, say. Then I equals AK2 equals constant. T4 where A equals area of cross-section, K equals radius of gyration, Appendix 2. If there are n columns, the total load sustained. But the weight of n columns equals constant. Nt2L equals W, say where ρ is the density of the material. So efficiency of structure. The parameter is known as a structure loading coefficient and depends solely upon the dimensions and loading of the structure. The parameter is called a material efficiency criterion and depends solely upon the physical characteristics of the material. For flat panels, the above arguments apply to a column whose thickness can be varied in 2 dimensions. The thickness of a flat panel can only be varied in 1 dimension. Suppose second moment of area per unit width of panel equals I equals const T3. For n panels, so const weight of n panels per unit width equals W. So efficiency again is a structure loading coefficient and is a material efficiency criterion. Suggestions for further study. At the end of the day, the best way to learn about structures is through observation and practical experience, that is, by looking at structures with a seeing eye and by making them and breaking them. Of course, the opportunities for the amateur to build real aeroplanes or bridges are likely to be rather limited, but do not be ashamed to play with Meccano, or even with old-fashioned building blocks. These things, incidentally, are much more instructive than the modern plastic toys which clip together in various ingenious ways. When you have built your bridge, load the thing up in a realistic way and see how it fails. You will probably be both surprised and disconcerted. When you have done this, the rather dry books on structures will seem a good deal more relevant. Although there is not much scope for the amateur bridge builder, it has often seemed to me that the field is wide open in biomechanics. This is a new subject about which very little is known, either by the engineers or by the biologists. It is very possible that there is an opportunity here for the enterprising amateur to make a name for himself. Though there are rather few good books, as yet, on biomechanics, there are any number on materials and elasticity. A small and admittedly arbitrary selection is given below. Books about materials. The Mechanical Properties of Matter, by Sir Alan Cottrell. John Wiley, current edition. Metals in the Service of Man, by W. Alexander and A. Street, Penguin Books, current edition. Engineering Metals and Their Alloys, by C. H. Salmons. Macmillan, New York, 1953. Materials in Industry, by W. J. Patton. Prentice Hall, 1968. The Structure and Properties of Materials, Volume 3 Mechanical Behavior, by H. W. Hayden, W. G. Moffat, and J. Wolfe. John Wiley, 1965. Fiber-Reinforced Materials Technology, by N. J. Parrott. Van Nostrand, 1972. Materials Science, by J. C. Anderson and K. D. Lever. Nelson, 1969. Elasticity and the Theory of Structures. Elements of the Mechanics of Materials, 2nd edition, by G. A. Paulson, Prentice Hall, 1966. The Strength of Materials, by Peter Black. Pergamon Press, 1966. History of the Strength of Materials, by S. P. Tymoshenko. McGraw-Hill, 1953. Philosophy of Structures, by E. Toroja, translated from the Spanish. University of California Press, 1962. Structure, by H. Werner Rosenthal. Macmillan, 1972. The Safety of Structures, by Sir Alfred Pugsley. Edward Arnold, 1966. The Analysis of Engineering Structures, by A. J. S. Pippard and Sir John Baker. Edward Arnold, current edition. Structural Concrete, by R. P. Johnson. McGraw-Hill, 1967. Beams and Frame Structures, by Jacques Heyman. Pergamon Press, 1964. Principles of Soil Mechanics, by R. F. Scott. Addison Wesley, 1965. The Steel Skeleton, 2 volumes, by Sir John Baker, M. Home, and J. Heyman. Cambridge University Press, 1960-65. Biomechanics. On Growth and Form, by Sir Darcy Thompson, abridged edition. Cambridge University Press, 1961. Biomechanics, by R. Neil Alexander. Chapman and Hall, 1975. Mechanical Design of Organisms, by S. A. Wainwright, W. D. Biggs, J. D. Curry and J. M. Gosline. Edward Arnold, 1976. Archery. Longbow, by Robert Hardy. Patrick Stevens, 1976. Building Materials Brickwork, by S. Smith. Macmillan, 1972. A History of Building Materials, by Norman Davy. Phoenix House, 1961. Materials of Construction, by R. C. Smith. McGraw-Hill, 1966. Stone for Building, by H. O'Neill. Heinemann, 1965. Commercial Timbers, 3rd edition, by F. H. Titmus. Technical Press, 1965. Architecture. There are many hundreds of books on architecture. I have picked out 2, almost at random. An Outline of European Architecture, by Nikolaus Pevsner. Penguin Books, current edition. The Appearance of Bridges, Ministry of Transport. HMSO, 1964. INDEX. ABE ADEEN, LOADAEROELASTCI TIAESTHETCSAGINCOURT, BATTLEOFAIRCRAFT, biplane ESCOMETCCONCORDENFOKKERGLIDENESMOSQUITIORENGTEFWOODENENEURISMSANTGONEARCHES, BRICKAN. DSTONEBOIDGESCOLLAPPSEOFCORBINESIOFFINISHITE Byzantine, Corinthian, Doric, Gothic, Modern, Mycenaean, Norman, Romanesque, ETRABEATEARTEISAUSTEN, JANE. Babel, Tower of ballistae bats beams cantilever hogging and sagging pre-stressed rolled steel joists simply supported stresses in wooden Benezet, St. Bias cut dresses Biggs, Professor W.D. Blown up structures Blythe, Dr. Henry Boyler's bursting of bonds, interatomic, distortion of bones calcium in properties of work of fracture bows, broken composite cross long Odysseus's Polyntonos Parthian rate of shooting strain energy in Tartar brazier buckling a bridges, arch, with suspended roadway Avignon bridges bowstring girder Britannia cast iron Clare Clifton. Hellgate Humber London Maidenhead Masonry Arch Menai Suspension Saltash San Luis Ray 7 Suspension Sydney Harbour Tacoma Narrows Thrust Lines in Trestle Brunei, Isambard Kingdom Brunel, Sir Markin Buttresses. Cable Cars Carthage, Siege of Catapults Ballista Efficiency of Palintonen Trebuchet Cat's Tails Corchi, Baron Augustine Cayley, Sir George Chaplin, Dr. Richard Cole, Effect of Pressure on Consumption of Coals, Captain Cowper Collagen Compression Failures, by Crushing by Buckling Con, Professor J. F. C. Coulomb, Charles Augustine de Cox, H.L. Dams Davy, Sir Humphrey de Havilland Aircraft Company. Dionysius. Discs, Slip Dixon, Professor McNeill Draconi Barges. École Polytechnique Egg Membrane, Fracture of Elastin Empire State Building Energy, Conservation of Definition of Potential Strain Units of Euler, Leonard Euler's Formula Euromachus Everest, Mount. Fatigue of Metals Finlay, James Flexural Center in Beams Fetuses Fracture, work of Bones Definition of Table of Variation with Tensile Strength Fracture Mechanics and Franklin, Benjamin Friars, Bridge Building. Galileo and Square Cube Law Sherman, Sophian Griffith Critical Crack Length Griffith Principal Guns, Bursting of Hagia Sophia Hall, Sir Arnold Heyman, Professor Jacques Hieroglyphics, Egyptian. Hooke, Robert Passim Hooke's Law Passim Huposometer. Ictinus Ignorance, Factor of Inglis, Professor C. E. Insulae, Roman. Joints, but welded in columns glued lapped in masonry to plastic in rigging riveted in roof trusses scarfed in tendons in tension members welded. Kennedy, Professor R. M. King's College Chapel Kipling, Rudyard. Lanchester, F. W. Larynx, in Men and Women Libel, Law of. Marriott, ed. Masts Material Efficiency Criteria Mathematics May, George Meredith, George Merson, Morin Michel, A. G. M. Middle Third Rule Monocox Muscle, Collagen in. As an energy converter energy dispersed in legs and arms mechanism of contraction strength of. Navia, Claude Louis Marie Henri Newton, Sir Isaac New York Trade Center. Odysseus. Payne, Thomas Palintonen Parthenon Paul, Professor J. P. Penelope Pipes Poisson, S.D. Poisson's Ratio Polygon, Funicular Pretlove, Dr. Tony Pterodactyls Pugsley, Sir Alfred Pyramid, Great. Resilience Reims Cathedral Rigging, of ships of young ladies riveted joints RNA DNA mechanism rockets roofs, supported archaic Greek over one's head vaulted roof trusses hammer beam rubber, strain energy storage stress strain curve of. Useless in biology work of fracture of. Sacrifices, human safety, factors of Sales Salisbury, Lord Salisbury Cathedral Sandwich Construction Shear, in dressmaking failure in solids modulus, G, definition of nature of relation with E and Q in rockets in sails in skin strain, G, definition of stress, N, definition of in worms ships, America, Yacht Beauty of Birkenhead, Troop Ship Captain, HMS. Chinese Cobra, HMS. Egyptian Great Eastern, SS. Greek Leviathan, SS. Majestic, RMS. Maltese River steamers sailing steam stresses in structure of Venetian Victory, HMS. Viking Wolf, HMS. Wooden. Shoot. Neville Salome, Tower of Skyamorphs skiing zone, Sir John Solomon, King Spaceframe Stevenson, Robert Strain. Shear, definition of tensile and compressive, definition of, expression of strain energy, as a cause of fracture, definition of storage capacity, table of units of strength, of a material, definition of solids, tables of a structure, definition of stress, factor shear, definition of tensile and compressive, definition of units of stress. Concentrations Passim How to live with stress trajectories stringed musical instruments structure loading coefficients Suez Canal surface tension surgery, orthopedic. Telford, Thomas Temple of the Olympian Zeus tendon, Achilles or calcaneal in bows in catapults in kangaroos in legs and arms strain energy in. Strength of test pieces, tensile Thompson, Sir Darcy thrust lines Passim in backbones in bridges torsion, in aircraft in bridges in cars in chickens in legs trees, deflections of growth of height of names of scarcity of strength of trusses, Borman bowstring fink hogging huposometer Pratt or how in shipbuilding Warren see also roof trusses tires. Vincent, Dr. Julian Vionet, Mademoiselle Vitruvius vocal cords voussoirs. Wagner tension field Wainwright, Professor Steve Wallace, Sir Barnes Watson, G.L. Welding wheels Wilkinson, John. Windows wine jars. Yachts, sea ships U Timber Young, Thomas Young's modulus, definition of table of units of Young's own definition of